Yeah, you can start, sir.
Okay, fine. So maybe all of us can mute so that everyone can listen to me. Okay. So good evening once again. I'm really happy to address you all in the online for this very beautiful session. Okay. The high speed IO session. Okay. I don't know whether I want to call this a session or the training, right? So the basic this one is like the intention of this one is to give some overall idea that okay, this is high speed IO today it is, and then to that where are we on the AT side? These are the basic intention of this training. So. The screen, the screen is coming. Right? Okay. I think that just a moment. The sharing there is some problem. Okay. Sharing on the people. What about now? Okay.
Now you can go to PPT mode.
Okay. So basically, like last week we did some session in the IT International Test Conference about this fast and furious high speed IO, and then for that we did a lot of homework, and we thought like we let us share the same thing to the team in our company wide to the teammates, and that is what the background of this training. Okay, so. One more thing that I would like to share with you is like we all know that high speed IO we have not done the latest projects or something, but we as a COE team we're doing homework on the PAM4 testing, and we have some instruments also in our lab. We are doing a lot of hands-on. And we are learning a lot using that instrument and on the academic side also. So this training will be sharing most of them with you people. Right? What I will be speaking this 5 days is like, okay, the first one is like introduction and recent trends, right? Meaning like why we are more interested in the HSIO space, and then what are the recent trends related to this HSIO, and then how we migrated from the LSIO to HSIO, and following that we will be discussing about like NRG signaling and its challenges. Meaning like we want to know like okay, what is the current HSIO terminologies and then challenges, everything, and then later on we want to move to the PAM4 signaling and its challenges. Our main intention. The slide is not moving.
No, sir, it's moving.
It's not moving. Yeah?
desktop full of
No, last time we shared the desktop. Now what is it you are seeing?
I'm seeing the agenda stuff. Give me a moment and just.
Yeah, guys, just a moment. Looks like my screen is not being shared properly.
Stop sharing. Share including desktop. Then I will proceed. Enable editing. And then food selection. In the screen share. In the screen share.
Where is that? So Gauri, what is that you are seeing?
I'm seeing Teams window.
What is it? What's happening?
Maybe I can share the English. Maybe you can speak.
Okay, that is not a problem.
Screen share. Including system variable, including system variable. Just log in. Yeah.
What is that you are seeing now?
Agenda slide.
Yeah. Okay, the one is
Two windows are being seen.
Duplicate slash. Yes, go to this.
Okay, are you able to see that? Yeah.
Yes.
Okay, for the confusions, okay. So we will be discussing about the PAM4 signaling and challenges, right, which is our prime intention of this training, right? And finally, we will be discussing about the challenges that we will have in the IT testing for PAM4 testing. Okay, so you may be wondering like what is PAM4 and all those stuff. Maybe we will discuss about the PAM4. Okay, just to start with, right, we may have to know like what is NRZ and PAM4. So far, we may not be very particular telling all the logic levels is NRZ or PAM4, right? So according to us in this context, right, what we call as NRZ is like whichever the digital signals, two voltage levels, meaning logic 0 and 1. Generally, in all our digital world, we always speak about the two levels, VOH, VOL, or VAL, VAH, right? Is what we call it as the NRZ. And in contrast with that, in regard to that, right?
ओपन हो जाएगा टाइप अ नेम की जगह
in regards to that, on the PAM4 side, right, we have PAM4, we have 4 voltage levels, right? In the digital world going forward, we'll be speaking about so what do you want?
If this is coming there, it has to be.
पास में लेफ्ट हैंड साइड पर आपके पास आएगा
Okay, so maybe we are slowly setting up things. Okay. Okay, what is PAM4 is PAM4 using 4 voltage levels, right, to represent 2-bit states. Like generally at a particular time we can represent 0, 0, 0, 1, 1, 1, 0, like any one of these. Whereas in the NRZ 0 or 1. Here it is like 4 different states, meaning like 4 different voltage levels we can speak in the PAM4. And the PAM4 is nothing but the pulse amplitude modulation, having 4 different states. Okay, this is what we are going to talk about today. Okay, just to warm up ourselves with some of the terminologies, right? I want to discuss some 5 minutes in our own language. What are the terminologies we use in this
पिक्चर पर माउस ले जाते ही एक ड्रॉप डाउन मेन्यू ओपन होगा इसमें अकाउंट ऑप्शन में अभी बेसिक दिख रहा है। यदि आप अपने अकाउंट को अपग्रेड करना चाहते हैं,
most of us will be very familiar what is IO, input output. So slowly in my language, in this saying, how I want to tell that IO is something like whichever is the outer layer of the SOC, right, which is really taking the input or output from the internal core to the external world. Okay. Some of the things that some qualities that IO should have is it should be really taking the internal voltage language to the external voltage languages, meaning internally in the SOC it may be working at 1.2 volt or 0.8 volt VDD, whereas the externally it may have to communicate through 3.3 volt VDD, and it should have enough drive strength to drive it until some length, right? And it should speak in that particular language, meaning like if it's the SPI or JTAG or something, it should use that protocol. So this is what broadly we want to see that, okay, what is IO? Input output is nothing but the periphery that taking the internal information to the external world, having some norms, especially having more drive strength and also in the different voltage level compared to the core voltage levels. Okay, just I want to quote that, okay, what is IO here? Okay. So, and we also know that, okay, what is parallel interface? Right, the DDR kind of interface, if you see, right, you will have n number of lanes, right, line, bus, whatever you call, right, as the parallel interfaces. Like data itself will have a lot of bits, right? It's maybe some 32 bits or 36 bits, something like that, right? Even sometimes some places like SDR memories has 16 bit or 8 bit, 32 bit, 36 bit, different width of the bus it has. So if you are going to communicate a particular given information through a bus, right, we call it as parallel interface. Okay. What we are going to talk today is mostly on the serial interface, not on the parallel interface. So what do we mean by serial interface? According to me, the serial is nothing but, right, transferring data which is supposed to be transferred through a bus with multiple input IO pins, right, input or output pins, should be traveled through a single line. Then it is called a serial interface. Meaning, you can see that here there's a data stream, right, out of the core with a parallel 8 bits, and I'm going to convert that 8 bits into serial way, right, in a single lane, right. Then this parallel to serial communication is happening, and is being told that it should be called a serial interface. Okay. So why we need to go to serial interface? This is also one of the question, right, that I will quote in the next slides, right? So you want to be assured, right? Okay, what is this parallel interface? What is the serial interface? And the serial interface does definitely will have a parallel interface internally, and then serial interface will communicate through a single lane. That is what we call a serial interface. What is the reason for going for serial interface? Always the advantage of taking more data with a lesser clock is with the parallel interface. But still, why people are moving to serial interface nowadays is like mainly because of this skew, the timing edges differences, the clock to data skew in the parallel interfaces are more. For example, like if you have DDR 32 bit and then the clock, the difference between the data and the clock for each data pin, right? 32 bit, if you have each bit with respect to clock, some bits may be earlier, some bits may be late, right? And then it's maybe difficult for you to find out a stroke point in the receiver point. Okay. As you move up and up in the speed, higher and higher speed, right, you will have a lot of difficulties to route the traces from one place to another place for the parallel interface. So because of these reasons, the people have moved from parallel interface to the serial interface recently. Okay, just to get to know that, okay, these all maybe knowing and familiar. This is not our intention today. Just to warm up you people, I want to quote all those terminologies like IO and parallel interface and serial interface. Okay. So then if you talk about serial interface, then you may have to talk about the SerDes. Okay. So what is SerDes? SerDes is nothing but serializer and deserializer. Okay. Serializer is like in the transmitter side, you may have to convert the parallel data into a serial bit stream. Right? You can see here, this one the parallel data here, and then the encoding logic to convert that. You want to know like which bit is MSB, which bit is LSB, and all those things, and then some gray coding or something or 8-bit encoding. All those things can be done here, and then converted into parallel to serial, and then through a line driver, right, to drive it, right, through particular one lane, right. This is what is the serializer architecture for any transmitter in the serial interface. This kind of typical architecture will be there. Similarly, the reverse way will be there in the receiver, which is like deserializer. So you will get a stream of bits in a single lane. After that, you will have like serial to parallel interface converter, like serial to parallel converters, right? And then a decoding logic, and then internally it will be parallel data to the core. So this is what typically a SerDes architecture, like serializer in the transmitter side, and then the deserializer in the receiver side. You can, if you have any doubts in between, feel free to raise it in the Q&A in the chat to the in the chat window, right? The Gauri will be making note of all these queries, and then in between I can stop for the Q&A, and I can answer for the Q&A logically after each portion. Okay. Okay, what is CDR? Right? You can see like there's one block diagram here as CDR here. CDR is like clock data recovery. Recovering the clock based on the data. So that is what the data recovery circuit. Okay. Recovering the clock from the data is the CDR circuit. This is also part of the deserializer, not the part of serializer, is a part of deserializer. So we get to know all those terminologies we will be using in the in this training session. The typical diagram of the CDR will look like this, right? You will give the input in this, and then it will have some phase vector, charge pump, low pass filter, VCO to get a clock out of the data stream, and it will use for the internal purpose of strobing the data coming, the data that is coming in to the receiver. Okay, this is what CDR. This one. I may be going very slow, right? So for the benefit of everyone to be in line with me, right? Especially first day, I may be very slow. Excuse me if you, some of you already knowing all these terminologies, because since this audience is like wide audience, right? I want to take you all to the same frequency of mind, what I'm telling. So for some, maybe it may be boring in the initial one, but definitely I believe like everyone will get some takeaway in this session. Okay, so what is that HSIO meaning? So now you know like what is serial interface, what is parallel interface, what is SerDes, what is CDR, right? All those terminologies, and then slowly getting into the HSIO, right? What is HSIO is like, it's a high-speed serial input-output interface, right? And then to me, right, the HSIO meaning, it should be a serial interface first of all, and it should be following some standard protocol, meaning like there are some protocols called PCIe, there are some SATA, the SGMI, right? All those things is part of the HSIO. right? Even the internet standards, the 10 gig standard, all those are coming under the HSIO space. Okay. And it should definitely, like if it is HSIO, we may recover the clock from the data, meaning like the clock is embedded in the data. We will have only one line for data transmission. So clock, there won't be any clock transmission along with the data. So these are the basic requirements of HSIO. Okay. So why we need to be familiar with HSIO? That's the main question. Like, all the way HSIO is there, and then why we need to be familiar with the HSIO is a big question, and especially now, right? And already most of us, like maybe some of this team working in the HSIO space, like PCIe and all, but still, now we are moving from the HSIO, normal HSIO with HSIO PAM4, right? Then the question is like why we need to be familiar with HSIO and why we need to be familiar with HSIO PAM4. So this is what the intention of this training. So this the whole intention of this training is 2 lines. Okay. Before I get into this one, I like to make my throat and my energy in the better way, right? We have recorded videos to play for you on the recent trend, right? Why to answer these 2 questions? Why we need to be familiar with HSIO and why we need to be particular with the HSIO PAM4. So I want to play a video. You would have heard all, I'm sure that you would have heard that about the artificial intelligence, the high speed input output, next generation wireless, all those stuff, right? Like all very fancy words that you may be hearing here and there. But anyhow, it is related to this high speed, the input and output. HSIO. Side and then move on to the PAM4. Before we get into the PAM4 challenges, we may have a short break and Q&A session 2. After that, we can go to the PAM4 signaling challenges. And finally, we will heard that about the artificial intelligence. Recently, you have heard all, I'm sure that you would have heard that about the artificial intelligence, the high speed input output, next generation wireless, all those stuffs, right? Like all very fancy words that you may be hearing here and there. But anyhow, it is related to this high speed, the input and output, HSIO, and how it is related to PAM4. Why we migrated from NRZ to PAM4, all those things we will be connecting here. If you thought about the artificial intelligence, everywhere we are talking about the drones and then the medical application, the AI, the smart cars and autonomous car, then augmented reality, everything. Like you can see, like all those stuffs, right, should work only if 2 things are possible. One is like the high computing capability with high memory bandwidth, and also the high-speed interfaces to transfer data from one place to another place. Especially like if you see like autonomous car, it has to transmit data through wireless, the real-time data to the network, and the network in turn it has to process some of the data and then get back to the car, which involves a lot of high-speed interfaces, right? And the speed that required nowadays is like not only just the high-speed interface with the NRC, it should be high-speed interface with the PAM4. Whenever I talk the high-speed interface here, it is high-speed interface with the PAM4. Even you can see like nowadays we use a lot of EV in the Corona time, the extensive usage in TV has happened in the last 3 months during our Corona lockdown period, right? We talk about like the full HD, ultra HD, and all those different terminologies when we go through this network service providers, the pamphlets, right? So what it means is like we are very much keen on getting high quality pictures, right? Either through the broadband or through the a USB stick or something, whatever it is. If you need high quality pictures, you may need the interface, HSIO interfaces to communicate from Ethernet route, the TV through Ethernet or through wireless or through the this one. So wherever it is, like some or other place, the HSIO is used. Without that, you cannot enjoy even this TV with high quality. Okay. In the data center case, right? We know like, okay, nowadays we sit in the home and then search something, whatever we need, right? In the Google, or we order a lot of things in the online during, especially in the Corona time, right? All those stuffs in the background use this data centers, and we need everything to be done in few seconds, right? So all those things indirectly uses the high-speed interfaces, especially nowadays with the PAN phone. Talk about the wireless, the tab or phone that we use in the home, right? And then we use that not only for speaking with somebody else, and then we are using for the Google search and then the streaming the video, right? Seeing a lot of videos in the WhatsApp, and then sometimes the real-time videos through Airtel network or some other iPhone applications and the Samsung applications. Different applications are there where we can do the video streaming online real time. And all those things, what it matters is if it is outside the home, most probably we're using the 4G, 5G networks through antenna, but in turn the antenna will be communicated to cloud or data centers through some high-speed networks, right, which involves Ethernet mainly. And if you're using the Wi-Fi, definitely you may be using the broadband, and then the broadband will be transferring data with very high speed. So all those in turn tells that there is high speed IO is involved on the path some or another way. You just recollect that, okay, like the 5G subs from different people. So the 5G is used for the massive internet IoT stuffs, and then the enhanced mobile broadband everywhere. And then a lot of people, if communicating to 5G, it is not only to stop only in the wireless. Once it's get into the base station, that it uses the Ethernet and other interfaces, right, internally, and it should be using the HSIO on the path once again, even though 5G talks about only the wireless between the antenna to the user equipment. In the background, once the 5G increases, 5G usage increases, in turn, the HSIO also will increase a lot. Okay. Another slide that I want to flash here with you people is like, it's not only the speed, the requirement is not only from the speed and also from the number of users. As the number of users are going up and up, the same network connection, right, should be turning data with very high speed. Right? But this graph tells that, okay, almost 53% of the world population already started using internet. So what it means is like a lot of data traffic, and you should have very high speed interfaces to move data from one place to another place, and the networks, right? So all converge that the requirement for high speed interfaces are very high in the coming days. Addition to that, the Corona kind of scenarios claiming for having people to work from home and order a lot of things from the online, and all those stuffs going to make the data usage more and more in the coming period, and the HSIO interface is like going to play a big role. And for us, like people like 80 people or testing people going to face a lot of challenges in the HSIO testing, especially the current HSIO testing, which is using the PAM4 interface. Before we get into the core HSIO, we want to slowly start from the LSIO and see like how some of the interfaces started as low speed and migrated into HSIO NRZ methods, and then later on to the PAM4 interfaces. You can see like a lot of interfaces, the low speed interfaces being flashed here, and then few such things are the SPI, the I2C, the UART, the CAN, MDIO, JTAG, and a lot more are there in the name of LSIO. And still we are using this all LSIO interfaces for different purposes. It has life even now, and then most of them is used for doing the register settings in the chips, or to access the registers, or to control a lot of stuff. And the CAN kind of interfaces are used in the autonomous cars, the automobile industry, and JTAG is used for the PC testing, and then also to some extent the SOC testing. But anyway, these are all like purely LSIO interfaces. There are a few more interfaces, such like PCIe kind of PCI interface, which started its journey from 33 megahertz, something like that. You can see like this 33 megahertz is the first the PCIe interface started with. After that, it moved to 66 megahertz clock and slowly ramped up until 266 megahertz. Later on, it jumped from 266 megahertz to 2.5 gigahertz clock, and now slowly we are seeing it is going to until 32 gigahertz clock in the PCIe Gen 5. Right? And the table on the left side, right, shows that like, the next generation is going to be PCIe Gen 6, right? And it's also going to be 32 gigahertz PAM4. But the noticeable point here is until the Gen 5, it is just the NRZ, whereas the Gen 6 moves to PAM4. So now you may be realizing why the PAM4 requirements are there and why we are talking about PAM4 in this session. It is being told or claimed that the PCI Express or the PCI itself, right, how it ramped up from one generation to another generation, and every time we used to claim that the bandwidth that is used in the PCI doubles every 3 years. That was the prediction, and we were seeing that trend before. But recently, we are seeing that it is no more 3 years time frame for one generation. It is much faster. That's why this curve, it very clearly tells that it's supposed to be like this. It is 3 years once it is doubling the bandwidth, but it is even faster, and the curve has been steeper and steeper now, making our life very challenging. That we want to make sure that ourselves ramped up and then keep ourselves ready for the high bandwidth requirement. And then the PAM4 kind of testing is going to hit us very soon, even this generation. Same applicable in the USB side, right? It started like very low speed, and you can see here like it is 12 Mbps is the first generation USB, whereas it slowly migrated from 12 Mbps to 400 Mbps, and then slowly it has come to 20 Gbps of Thunderbolt 2, and then the started getting into 40 Gbps trend now. So you can see, you can imagine that how it has ramped up from 12 Mbps to 40 Mbps, and the testing challenges that we are going to have, right, related to Thunderbolt 3 testing, which is also operating with the PAM4 testing. Same with Ethernet valuation. Like Ethernet, right, we all know that it started something like in the 10 base T speed, and then slowly become like 100 base T and then 1000 base T, something like that. And then now people are talking about 400 G, and even already 800 G also being analyzed by so many companies to implement. One thing that you want to note it down here is, unlike other interfaces, the Ethernet is very keen on using the PAM4 interface more than NRC in all the recent generations. So it tells that the PAM4 is really required and highly required, and we need to ramp up ourselves on the PAM4 testing and be ready with its challenges. Let's understand the challenges of the PAM4 using this session. This is the summary of the interface that we talked about. So you can see like the latest generations are all using the PAM4, whereas the previous generation of the PCI Gen, USB, and the Ethernet all were using the NRZ. As a test engineer or as a ATE test engineer, how it matters for me. If I have a situation where C is going to be very high speed and low drive outputs, the testing is going to be very challenging. If it is very high current and high precision measurements are involved, then it's going to be much more challenging for me. And if there are a lot of noise, low noise requirements, right? Nowadays the voltage levels are coming down and shrinking, so the low noise requirements are more and more, so it's becoming more challenging for the ATE. Even if you want to introduce a lot of onboard components to substitute some of the work that being done by the instruments, introducing those onboard components will also make the ATE engineer very challenging. On top of that, the ATE engineer generally like to test more DUTs parallelly, and if that's going to be the case, is also going to be challenging for us. Right? And yes, you know that the devices are coming up with a lot of balls, especially the BGS side, like in couple of thousands of balls, and obviously it's going to be very fine pitch, making us to be in trouble for routing the traces to the VGA and maintaining this high impedance, maintaining its impedance without mismatches. But it's all those things going to make us very challenging. It is very common that, okay, all these variables will make the ATE engineer job very challenging. Let's say if it is HSIO, normal HSIO with NRC, what will happen? The cartoon is mimicking my expression here. Okay. The additional challenge involved for recent HSIO, I don't think I can convey in one slide. I have a big list to convey you people, which we will be discussing soon. More than that, more than the HSIO NRZ, right? If we go for PAM4 testing, HSIO using the PAM4, then it is multi-dimensional challenges. Right? You can see that the NRZ eye diagram will be looking like this typically, whereas the PAM4 eye diagram will look like this typically, whereas, right, making our life very miserable to test this kind of eye diagrams and to just get this kind of eye diagrams in our measurement instrument. Right? So what are the challenges involved? This also will be discussed in this session. Slowly, we will take you to the HSIO challenges and later on to the PAM4 challenges and some of the proposed solutions available for the PAM4 to educate you on this. Okay, so we are back from the video. Hope you all can hear me.
Unmute பண்ணிட்டேன். Unmute பண்ணிட்டேன்.
You are able to hear me?
Yes, sir.
Okay. So what I basically was trying to say in the video is like the recent trends, right? Like the artificial intelligence and the 5G stuff and then the data centers and then the search engines, whatever it is, right? The cloud, all those things indirectly using the HSIO in this path, some or other way, right? Without HSIO interface, nothing can exist, right? Something like a, if you don't have the HSIO with a high speed, it will look like a Madiwala bridge, right? Now I don't know the last 3 months how the Madiwala bridge is looking now, but earlier I know that from the electricity we take only 8 minutes or 7 minutes to go to the Madiwala bridge, and from the Madiwala bridge we will be there for 2 hours. Okay. So it's basically right. We have a high-speed link from the electricity to Madiwala, right? And then from Madiwala to this one, right? The city, right? We have a very low-speed link, right? That's the reason that we spend hours and hours in the Madiwala, right? Well, this one. So the same scenario you may be seeing if the HSIO space is not improving, and if you just bring in the 5G and other stuff, so you will have the same scenario. That's what the message, right? So even though our intention is to train the PAM4 in this training session, I want to make sure that and the terminology that is used in the NRZ HSIO first. Right? That is the first few sessions we will discuss more about the NRZ. And then once you are familiar with all the terminologies, or maybe a little bit, right? I may not be going through full 100% all the terminologies or something, but decent terminologies I want to make sure that you all are aware before we talk about the PAM4. So then first 4-5 hours we will discuss about the NRZ. Okay. So far if anyone has any question, maybe you can stop me by putting your question in the chat window. Okay. Let me share one more time my are you able to see my screen?
Yes, sir.
You're able to see my screen? Sorry. What do you see?
I'm seeing the NRZ title slide.
Okay. So basically what I was telling is like let's understand the NRZ HSIO setup first. And later on we will get into the PAM4. So this NRZ itself, a lot of terminologies are involved. Some of you may not be familiar with the NRZ terminologies used in the HSIO. So once we become familiar with the NRZ terminologies, we will move to the PAM4 terminologies. How it is also easy for us to relate NRZ and PAM4 hand in hand. Okay. So to start with, I will discuss something on the different setups available on the TX and RX side of the HSIO and RZ. They're all related to HSIO only, not like normal one. And we want to touch base on some of the eye diagram formation techniques, like how it is formed, and then the eye parameters involved, and also not only eye parameters. Most of you may be heard about the eye diagram and eye parameters, but half of the crowd here, I believe that might not have heard about something terminology is called eye counter. Okay, eye counter and the eye monitor and bathtub, right? All those terminologies. Some may might have heard about this terminology. Some may not have heard. Most of you may have heard about the eye diagram, but not about the eye counter and eye monitor. So we will discuss about all those terminologies in the NRZ and slightly get familiar with some of the parameters measured through this concept. Okay. The transmitter, let's say if you want to test one transmitter, if your chip that has some TX and I want to test it the TX parameters, right? What generally we will do is like we will use something like this, the setup one here, right? the BERT or the ATE will be used, right? The BERT is nothing but the bit error rate or bit error ratio tester. BERT is like bit error uh, ratio tester, which will be used for generating some pattern and to receive the pattern from the that to compare with. Right? It will compare like what are the bits that I have transmitted and what are the bits that I have received, and compare like with the received data bits with respect to the sent data bits. So this is what general typical setup of the transmitter. So we will be using like BERT again in this session. So good to know about the BERT, right? Okay. So if in our ATE setup, we may have to do the same thing, mimic same thing with the ATE. Right? We may have to use pattern generator to send the pattern and receive the pattern from the DUT and compare the sent bit versus the received bits. That's what a common thing that in the ATE we used to do. So this is one kind of setup we use for the HSIO testing the TX path, not the RX path. Okay. The same thing can be done in a different way. If you want to measure so many parametric measurements, we can have one more setup. Okay. This diagram tells that the TX output from the DAT can be connected to two different instruments. One can be BERT and another can be DSO. DSO means the digital sampling oscilloscope. Okay. Hope you might have heard, all of you might have heard about the oscilloscope. So the blue box is the oscilloscope, whereas this diagram is the BERT, right? The same thing can be mimicked in the ATE setup, right? For this, right, we may have to use some in the pin electronics and use some digitizer. Hope you all know about the ATE digitizer, which will be used for digitizing the signal. So it should be replaced, like it should have a front end circuit with the ADC, and then it should have a DSP also. Okay. So this kind of setup will be used right for the TX testing. One for the functional level of testing, another for the parametric level of testing. So same can be made with the ATE also, using the pin electronics card and the digitizer. That was the message here. These are all common. You may be knowing all those things, but this is just to bring you on par with what we are talking about. Okay. So there may be one more setup called like, okay, in the bench side, we call it as protocol. Let's say you want to test the Ethernet chip, you want to use some protocol analyzer which understands the Ethernet standard. Right? The patterns, the packet that is being transmitted by the TX should be understood by the receiver, which we call it as protocol analyzer. The same thing also can be mimicked in the ATE environment using some post-processing routines. Right? You can use comparator logic in the pin electronics card, and we want to capture the data using the dig capture, and you can process through the DSP in the ATE. So this also can be mimicked with the ATE. It's not straightforward. I will tell you like what is straightforward, what is not straightforward, what difficulties we have in all those things. Logically speaking, all those things can be mimicked in the ATE for all the HSIO. This is what the message here. Gauri, so far any queries? Anyone until now?
No, sir. No one has raised queries.
Okay, so hope people are in line with me, or at least some acknowledgement you can give that, okay, are you able to understand, appreciate or not, right? Maybe people can feel free to give comments. Am I going faster? Am I going slower? All those things, very much slow. Feel free to comment it. Anyway, it's like, as you know, I have taken so many sessions, company-wide sessions in the Agni room before in the Dassault. But anyways, new experience for me to take the online session without seeing all of your faces. and judge like okay whether you are really understanding or not, all those things, right? It's very new experience. It looks like a half duplex, right? It's not a full duplex training, it's a half duplex training, right? So feel free to put your comment, right? And also hope it is an evening time, everyone can have tea also parallelly to make you awake, right, throughout the session. Okay, feel free to have tea also. So coming to the receiver setup. So receiver setup also can have the same kind of setup what the TX has. Board setup in the bench, and then it can be replaced with the ATE in our environment because it's basically loop back testing between the duct RX and TX. So board will be using its own pattern PRBS generator to generate a pattern and pump to the duct RX, and the duct TX will give back the output using the loop back, and then the board will take this one. So same thing can be mimicked by the ATE using the pin card on the transmitter side and receiver side. Logically, I won't tell that okay, it's a full replacement. It's logically supposed to. Okay. So another setup for the receiver can look like this. Right? If you don't have the loop back in the duct, right? If you want to test it only the RX, it can look like this. Your duct can look like this. Internally, it may have some PRBS generator, and if you the transmitter, the board, if it having some PRBS generator and pumping out the data, and there will be a comparator logic in the RX to detect this data, and indirectly you can have some logic, error detector logic in the receiver to check it, right? Whether the receiver is able to detect all the data that is transmitted by the board, right? This portion also can be replaced by the ATE, by the pin card, speed card. Okay, logically, all of like I'm just going through logic. We have a lot of practical issues that we will discuss over a period, like in the coming days, not today, but in the coming days we will discuss about that. But logically, right, this you can replace the HSIO testing using the ATE, which will be done by the board and the bench setup. As long as you have a PRBS generator in the receiver and also the error detector circuit in the receiver, but you don't have the loopback provision. If the loopback provision is there, you can very well use the setup 1 for the receiver testing. Okay, one more setup. This setup is a very tricky setup, right? Most of you in the quality team you may be aware. What kind of setup is like, okay, let's say you have the duct with the ARM processor or something, right? And then if you have some protocol generator outside or PRBS generator, in fact, this can be a PRBS generator also. It can be either PRBS generator or the protocol generator. And if you give the output from that instrument to the RX of the duct, right? From the RX, you can use some CPU program in the inside the duct. If you have your duct has processor, you can use CPU program. Some people call as funk test, right? In the language of AMD or something, they call it as a funk test, and then the language of Qualcomm, I believe, it is called CPU test, I believe. Right. So using the CPU program, you can judge whatever the data that is coming in through RX. Is it meeting the whatever the data that is being pumped out by the PRBS generator? So and then that you can pass on the pass fail flag from the CPU program to through some GPIO to the machine to know whether it's a pass or fail. Okay. So these are the different setups that we can have in the receiver and transmitter testing of HSIO in general, in the NRZ, even in the PAM4. This is not going to widely change for the NRZ or PAM4. Okay. Any questions? Feel free to ask questions. Stop me. Like, let's not. I'm not in the mood of rushing and then completing. I want to go much slower. Right? Any questions? Put in the chat box. I'll be happy to get stopped in between and then answer you.
Sir, actually, we have one question.
Yeah, go ahead.
How to generate and capture digital signals for 4 levels?
How to generate and capture signals for 4 levels?
Yes.
Okay, very good. But this question is a very early question. That is what the whole session all about, right? So I will answer on Friday. Definitely you will get answer for this, right? And it's not straightforward way. Like there are indirect ways how to generate all those. That was a big challenge, you know. Based on this question, like when I first initially heard about PAM4, the first question for me it got hit is this question only. And then we were doing a lot of homework all the days, right, to find out answer for this question. So definitely don't worry, I will share this answer, but most probably on Friday you may get this answer, or Thursday you may get this answer. Okay. We have challenges to generate these 4 levels, but it's possible to generate. As of now, maybe I'll limit my answer to that. Definitely you will get some answer, concrete answer on Thursday for this question. Okay. So any other questions, Gauri?
No, no more, sir.
Okay. So anyway, so we'll slowly move into that in the PAM4 direction. Before that, right, maybe that's what I want to sing up with you what are the terminologies we have on the NRA side before we get into the PAM4. So that's what the ultimate aim. So we will discuss about the eye diagram first, and then the eye color, eye monitor, and all those stuff today. And then we will go to the different terminologies of NRC. Right? It will be easily it may take today and tomorrow to complete the NRC stuffs, right? And then later on we will discuss about the PAM. Okay. So most of half of the crowd here, as I quoted, like you may be knowing about the eye diagram, how it is formed. Right, in the especially like we may be seeing the eye diagram in the bench instrument, but in the tester it is not so easy to do the eye diagram. To form the eye diagram itself it may be challenging, right? So first of all, you may want to know like what is eye diagram. Right, you can very well tell here like eye diagram is used in the electrical engineering to set a good idea of signal quality with infinite persistence. Right? Meaning, in general, the eye diagram looks like this, right? And what is the difference between this eye diagram and the non-digital signal is? Basically, if in the layman terminology, I will tell like, okay, I will chop the bit stream, the digital signal, the digital output signal that is transmitted by the TX, I will chop it and overlay one after another. That is what the eye diagram. I'll repeat, right? Please make sure that you understand this. So anyone, I don't want even one person not to understand this eye diagram in this crowd. It is very important, right? Half of the crowd you may be knowing, but who does not know or understand, please stop me here. Eye diagram is something like the TX output, chopping the TX output for a window and overlapping again, right, is called as eye diagram. Okay, but why we want to do this? Why I want to chop it and then overlay again? That's maybe a good question, right? So why I want to chop it is like, okay, if I see the output diagram, output waveform from the TX, I may get a line like this, or like this, or like this. Here I will get some voltage level. This is like basically voltage level. This may be 400 millivolt, this may be 500 millivolt, this may be 600 millivolt. So each time when I get a high level, I may be getting the VOH level of 400 or 450 or 300. But I don't know how much oscillation it will do. Right? To know the full oscillations on the high level, I want to overlay and then see like how good this width is. Right? It's basically to understand the waveform the TX output in a better way. That is what, nothing more than that. It is like the transmitter output is not going to give you eye diagram or something. Transmitter output is going to give you a normal digital stream output, whereas we will chop it and overlay to make things better in our life, to understand different parameters, to judge whether it will work or it will be understood the same way by the RX. Whatever the way the TX is communicating the same way, right? Is it going to be understood by the RX or not? That is what it is being analyzed through the eye diagram. Okay, hope you all understand. So this diagram you can give much better view, right? You will be knowing like, okay, this is the signal level, and then what is the noise that it has between different cycle, and cycle transitions every time between one cycle where it is transiting. If it's differential pair, the low and the P and N, is it crossing in the center point or not? Right. Likewise, you can see so many different data by doing this exercise of cutting or chopping the waveform and overlaying. Okay, that is what it is quoted here. Gauri has done a small video here for the eye diagram. Maybe let me see whether I can share eye diagram formation. Are you able to see?
No.
No one.
Gauri?
Yes, this is the presentation, not the video.
Sorry.
Only the presentation is displayed as
Only
usual.
the slide, not the video.
You're saying only this slide, okay.
Yes, yes.
Just, you know.
No, sir. You can click that title.
Write a little bit.
Title, huh?
Okay. You have to share your stuff. Share your this program also. Share பண்ணலாம்.
One second, let me share once again.
Include system. Gauri, there is no voice on this, right?
There is no audio for this.
Okay.
What about now?
Yeah.
Yes.
You can speak.
Okay, so you can see like the each portion how it is added here. So very important. You want to understand this how this eye diagram is formed by chopping each cycle. It's not exactly one cycle. It is like there are some formula like the more than one UA should be captured. Right? Maybe let me play one more time. Okay, hope you all got something.
Stop share number. You don't share number. The more like my was.
Okay, one second. This one, right?
Stop sharing. presentation. Okay.
So you will see my screen, Gauri?
Yes, yes.
Yes.
Okay. So anybody has any question on the eye formation? It's very important topic that you want to appreciate throughout the session. All the 5-day session is basically using this eye diagram as a base, right? That's why we felt that we want to insist here. Anyone has any questions on the eye diagram, please feel to raise it in the chat. Okay. So you can see the eye diagram here in this the oscilloscope also. Basically, this is like one UA window, unit interval, meaning like for the period that is for one side, one bit. Right? The UA, like let's say if it is 1 gigabits per second. 1 gigabits is something like for 1 nanosecond, 1 bit. So the UA of the 1 gigabits per second is 1 nanosecond. So this period should be this crossing point to this crossing point should be 1 nanosecond. Right? So basically, for the eye diagram, the chopping has to be done more than 1 UA. That's very mandatory. Okay. So to do this eye diagram, you want to use something like in the scope, and if you want to use, if you want to test the BER, bit error rate, you want to use a setup like this. The same setup was shown before, but it is zoomed in on the dot side. Right? The TX of the board should be giving the input to the dot receiver, and these all terminologies will be discussed in the future, like what is CTLE, what is DFE, what is slicer, what is clock recovery, what is this liner, right? All those things we are going to discuss in future. Maybe don't be hurry to understand all those things, right? We definitely will this one. So there's the BR setup will look like this. The eye diagram will look like this. The message I want to communicate through this slide. And there is one more terminology we call it as FFE. This also will be discussed in the following sessions. Okay. So if you want to look at this, right, the whole things we will be discussing in the future sessions. Get to know that, okay, this kind of setup is there for the SSIO TX. Okay. So getting to the eye parameters. What are the parameters? If you see, like in the eye parameters, I was thinking before knowing the eye parameter, okay, eye parameter may be 1 or 2 in the vertical way. And horizontal way, we may measure some timing parameter, we may measure some voltage. That's what in the generally, in the normal interfaces, we measure VOL, VOH, right? Or we will measure like VOD in the differential pairs, right? And then we will be worried about the timing, jitter, right? Whereas we see that in the HSIO, no, the same thing only we are measuring in the different names, right? And we are not measuring for one cycle. In the LSIO, we measure that the VOH for one particular cycle, not for so many cycles, right? We will not be too much worried about measuring the VOH for each different bits, right? Whereas here, through the eye diagram, we are measuring the VOH or VOL or VOD, right? The difference, output difference voltage between P and N in the different names. Right? Why is that? I'm not going to discuss about that. At least I will discuss about like what are the different parameters being measured in the eye and how it is going to make our life tougher and tougher if we go to the PAM4. That's what the intention of touching base on these parameters. Okay. So if you see this NRC eye parameters, right, we may have to measure all these parameters: 1 level, 0 level, waveform top, waveform base, maximum voltage, minimum voltage, peak to peak amplitude, crossing percentage, the P and N where it is crossing, and how much it is varying. There is just a VOL or VOD, whatever it is. For each cycle, it may be different VOD, different this one. So we may have to measure the noise involved in VOD across different cycles, and then compare to the noise. What is the signal to noise ratio, the extension ratio? So many terminologies, like some might have heard about this, some may not have, but don't worry, we will discuss at least few here. Okay, but at least get to know that we have a lot of parameters in the eye where we may have to measure all these parameters right? To make sure that the TX is giving the right output, and then to make sure that whatever the output that TX is giving, RX will be in a position to understand. That is what more important. So because unless you verify all these parameters, you cannot ensure that the RX will not understand what the TX is transmitting. Okay, first thing that we will like to discuss is the jitter. Right, the jittery. Jittery is something like in the English literature you can call it wavering. Right, it's supposed to do something, right? Or maybe I'm supposed to tell something, and then if I'm going on varying here and there, right? It's a wavering thing, right? So same thing, right? Any signal is supposed to change at a particular given point of time. So given point of time, you want to change it, whereas it will not. Right? For example, in the 1 gigabits per second, right? For every 1 nanosecond, the bit should change. Okay. Whereas it will not change at the same exact 1 nanosecond. It may be changing at 0.98 nanosecond or at 1.1 nanosecond. Or at one time it may be 1.1, one time it may be 1.11, one time it may be 0.98, it is 1.9 itself. So we may have to be interested to know like when it is really changing, right, on the different cycle. So that is what it is called as jitter. So in a formal way, jitter is the variation in the signal's timing from its nominal value. Nominal value means nominal ideal cycle value. That's what we mean by nominal value. Okay. So in turn, it will tell that if it is not happening in this nominal value, it has some phase difference or period difference, width difference, duty cycle difference, whatever it is. Any of this difference will create the jitter. The jitter is a very broad term. Okay. Broad term to discuss. And there are a lot of different jitter, varieties of jitter, types of jitter. Okay. This also you may have to slightly understand. What is that? Jitter. I told you jitter. Jitter can be broadly classified into deterministic jitter and random jitter. What do you mean by that? Random jitter is something like you cannot predict. No rhythm in that. When it will come, when it will not come, right? You cannot predict. That is what random jitter. And deterministic jitter is something like you can predict or you can give some theory behind that, why it is coming. Right? Please listen. Like random jitter is something like jitter is a jitter. The background of the jitter, right, can be classified into two, and as long as you can give some explanation, correlate with some of the phenomena of the transmitter or somewhere else, then it is called as deterministic jitter. Whereas wherever you are not able to correlate with some interference or some or other way on the theory side, that is called as random jitter. You cannot predict when it will come. So be clear on this. Inside the deterministic jitter, you can still classify into two ways. One is like data dependent jitter, meaning if I send 110, right, it may be different. If I send like 001, the jitter may be different. So the jitter is like, it may be like continuous 0, after that if you send 1, the jitter will be different, or 101010 if you send, the jitter may be different. So it based on the data bits, the style of the data bits, the consecutive bits, effect consecutive bits in the jitter, it is called as data dependent jitter, DDJ. So you can tell that, okay, if I send this kind of data stream, this kind of jitter will be there. So as long as you can tell that theory, right, that is what data dependent jitter. Okay. There's another jitter called uncorrelated with data. Okay. So uncorrelated means it is independent of the data, but still you can tell some theory. Right. What theory you can tell? Sometimes, right, there will be a noise in the PLL. PLL will give clock over a period 1000 cycle once. It will give some small deviation in the clock. So that will be mimicked in the reflected in the data that is transmitted by the TX. If you are using some PLL in the SerDes, you will be using PLL, right? PLL or DLL will be used in the TX path on the SerDes, and that PLL has some noise or some jitter over a 1000 cycle or 100 cycle or 150 cycle once. That also will be reflected in the jitter of the TX output, right? So that kind of jitter, which is created by the PLL kind of this one block inside the TX circuit is called as uncorrelated jitter with the data, because it is common irrespective of whatever the data pattern. Right? Hope you appreciate here. So uncorrelated data may be because of the clock in the PLL, right? Or sometimes it may be the crosstalk, right? That also even that is classified still further, non-periodic and periodic. Okay. What do you mean by that is, like, periodic jitter is something like you can tell that every 10 nanoseconds, every 15 nanoseconds, this kind of jitter because of the PLL or crosstalk it's coming. Right? If you are going to claim that no, this like already there is a thermal noise in the PLL, right? Or something like maybe may not be it may be different. Let's say like you have some noise which is not with the same clock domain of what you are transmitting. Right? It may not be periodic. Let's not confuse too much. But anyway, as long as the jitter, right, you can tell that every 10 cycles it is coming or every 100 cycle it is coming, then it's a periodic jitter. Whereas you cannot correlate with the number of cycles, the jitter, then it is non-periodic. Okay, so you want to be clear, like first category is deterministic and random jitter. In the deterministic, data dependent and non-data dependent. In the data dependent, you have non-periodic with respect to your TX and periodic with respect to the TX clock. There may be a number of reasons why it is created, because of the clock or because of the crosstalk internally, and sometimes maybe crosstalk may happen externally in the board or sometime, and that may not be in sync with the same period of TX. For example, if one more lane, right, there is the one system and another system is there where that system is working in different frequency, and that data will have the crosstalk effect of crosstalk effect to this line. So then it will be definitely a non-periodic because it depends on the data on the other lane. Okay, so you are able to appreciate it, right? In the data dependent jitter also, you have two things. One is like duty cycle distortion, right? If the data pattern changes, there will be changes in the duty cycle. And there will be one more category, inter-symbol interference, meaning based on the data bits, as I quoted before, if your data bit is like 1, 1, 1, 1, 1 and then 0, right, the jitter may be different, whereas like it may be 0, 0, 0, 0 and then 1, the jitter may be different, right? So it's basically telling that the bit stream that is traveled before this particular bit has the impact in the jitter, right? That is what we call it as inter-symbol interference, meaning like the bits that is traveled upfront before this bit has some impact on the jitter. That is what inter-symbol interference. Okay, where and all it can come. Before that, maybe if you are interested, I can tell about the random jitter a little bit more. Random jitter is created mainly because of the thermal noise, and short noise they call, right? So, which is very difficult to predict, right? But even though you don't know the theory why it is coming, But still, if we over a period, right? If you capture the eye diagram for 1 second or something, right? Then you can tell that okay, this place is like okay, this is the jitter. Because we are not only worried about the theory behind the jitter, we are worried about the real jitter, right? If you know the theory, we can we want to categorize into deterministic jitter and random jitter. Random jitter is that we may not be knowing the theory. Deterministic jitter, you may be knowing the theory. By knowing the theory, you can attack one or other way. That is why it is we are classified into two different classifications. Okay. So where does this jitter come from? Okay. So you have in a path, you have a transmitter and the channel and then the receiver. The jitter can occur anywhere. The jitter can be originated from the transmitter itself, right? What we discussed like thermal noise or the random jitter, the duty cycle distortion, right? The power supply noise, right? Power supply noise will give both random jitter and then the periodic jitter, right? On-chip coupling, also periodic jitter. And the mostly channel will give the inter-symbol interference, lossy interconnect, right? If you have a cable or the PCB trace which is poor for this particular speed of the transmission, it will create a lot of ISI and impedance mismatches, right? And sometimes because of the some other lane that is going close to this may create also some interference in this lane. Because of that, you may get some jitter, right? And then the receiver also may have its own jitter. Okay, the jitter can occur in the transmitter, jitter can be introduced in the lane, in the line, in the transmission media, right? Or it can occur in the receiver. This is what, these are the places where the jitter can occur. Okay, so these are the different types of jitter, maybe in the broad way. But when you measure, right, you will not be measuring like, okay, deterministic jitter or this one, right? There are ways how to measure this deterministic jitter and random jitter. And jitter is measured through different parameters. One is like periodic jitter, cycle to cycle jitter. Physically look like when you measure, no, that is called in these names. Let's not get confused between the deterministic jitter and the random jitter and compare the periodic jitter, the cycle to cycle jitter, all those terms. This is the measurement way. The periodic jitter, cycle to cycle jitter, long term jitter, and all, right? It's the way how you measure the jitter, whereas the theory behind that, how it is classified and all those things, is the previous slide. So don't get confused because of that. Periodic jitter, I'm not going to discuss thoroughly on these parameters, but just to get to know that, okay, long-term jitter is like accumulating the cycle-to-cycle difference for long time, and the plus and minus is the long-term jitter, whereas the cycle-to-cycle jitter is every cycle you measure, like where is this change is happening. Okay, that is what is the cycle-to-cycle jitter. Let me skip this slide. Okay, so before I get into the noise, right? Any questions on the jitter? Maybe let me also have some tea. Maybe you will also can post me the question and answers in the so far. What are the questions and answers? Otherwise, I expect the comment from everybody that okay, so far how is this one? Right? What is the score that you give, like for your understanding? Don't rate my this one. You can give chat in the chat window. Can you give like okay, so far what is your understanding? Out of 10, if you understood thoroughly so far, you can give 10. If you don't understand anything, you give 0. Can I get the please? Can you give me the this one the scoring for so far what you understood so that I can make it faster or slower? Let me give 2 minutes for everyone to give that scoring. With you, are you there? And anyone want to comment here, you can unmute and then comment. Like so far, is it really going slow or fast? Are you able to appreciate or not? Right? Or maybe our team members who in our team who are all there, see?
The managers are there and the Prashant.
I mean, like to get some comments before I proceed because the efforts that we are taking here, no, it's enormous. We want to make sure that you will appreciate something and take away, right? Prabhu, can you comment something?
Okay, Jagdish, I'll take the first strike.
Okay, who is this? Sorry.
Prasad.
Prasad, okay, yeah, go ahead, Prasad, yeah.
Looks like people are hesitant. Anyway, this is going good. I mean, at least we are getting to know some of very basic things to a certain level before we start ramping up onto the exact HSIO concepts and all. So, as so far, it is fine, no issue. At least to get to know jitter and some of this noise and how do we do all those bit error concepts and even your LSIO, some of the interface basics of the interfaces. So all these things were fine. So from my side, I don't have any comments as such beyond this.
Okay, so according to you, go in the same style.
Yes, for to me it looks good.
Okay, because this is the first time we are doing in the online session for the company-wide people, no? So it may be like, I won't tell that, okay, I am a perfect teacher or maybe the session is very ideal situation or something. We may have, feel free to tell your comment. No, don't feel bad about telling the comment, right? I'll be happy to hear from you and then improve, right? Feedback is the only mechanism where we can improve in the next session. Right. If you don't give it, then I will assume that everything is fine and then will go in the same way. Don't allow me to do that. If you feel like you want to be in a different, you want the session to be a different way, feel free to comment. Okay. So anyone else, maybe in the junior level, anyone?
Jagdish, with you here. Jagdish wanted to check with you. Later on, you're going into the AT stuff, right? Like after we finish the concepts wise, the AT part will be what you will be covering later on, right?
Yes, definitely. Yes.
Okay, yeah. Because, like for example, we were doing a project which we wanted to do PAM4, but then I think unless and until we use the specific instrument on any AT, it is not possible, right? Using our current level, so we need the specialist instrument. So we will be touching upon that, right?
Definitely, yeah.
Okay,
so
fine,
you may have to wait until Thursday or Friday for that.
Okay, fine, yeah. I mean,
yeah. Basically, what happened with you, like we were trying to tell people, right, okay, about power or something, but then we failed to we may have to go back and then try tell them something. Likewise, we went back, and then now we are right almost like we thought we need 10 hours or so to tell about PAM4. Christy, for the PAM4 is at least 10 hour session.
Okay, got it. So all the basics of the eye and jitter and the high-speed transmission you are covering first, and then we start going into PAM4, right?
Yeah, definitely. Yeah. So basically, one of the toughest topic we felt is equalizer.
Correct. Yes.
Right? Mainly that 80 people felt that the equalizer part we are very poor. Eye diagram, at least half of the crowd maybe here and there might have heard about all those terminologies.
Correct.
Right? But 80 side, we feel that equalizer is a major topic which no clue for most other people.
Correct. Yes, I agree.
Okay, so tomorrow is fully focused on the equalizer.
Okay. Yeah, I think so far fine. The basics, whatever you covered today, that was all good. I mean, some of the guys who are there from my team, they are some of the high-speed guys themselves. So for them, it might be more basic than what is needed, but that's fine because the larger audience is not high-speed IO guys. They're either digital guys, LSIO guys, which are not experienced. So for them, it's perfectly fine for now, no problems. I think the high-speed guys who are attending from my team, maybe second or third session onwards, like you said, equalizer will be what is more relevant to them.
Yeah, definitely. For even today also they should have some takeaway. But I'm sure that, right? I don't know how many of you heard about the eye counter. Okay.
No,
and
that
about the eye counter, eye monitor. Okay, these are the terminologies we are going to touch today also.
Okay, fine. Then good. Yeah, that's also new.
Okay, we have some demo also to show using the multi-lane instrument, how to capture the eye diagram.
Cool.
Okay.
Yeah.
Okay.
But I couldn't reply to you earlier. I know you called my name. My laptop is dead, so I'm using the
No
mobile
problem.
to log in. So that's it.
Okay, no problem. Okay, so let me continue. Okay, so in the eye diagram, right, as I quoted last time, if generally in the LSIO part, we will measure VOH, VOL, or VOD, right? Whereas you may be you may be interested to know the VOH or VOL or VOD on the different cycles. Right, with one cycle, the cycle number 1, what is the VOD, and the cycle number 10, what is the VOD, or cycle number 100, what is the VOD, right? If it is changing and it is playing a big role, because normally the 3.3 volt logic, what we are discussing, typically we will working no, more than 2.4 volt until 3.3 volt, it is VOH. Right. So you have a margin almost close to 1 volt margin you have. So you may not be so much worried. Whereas in the HSIO space, right, the total VOD will be like 200 millivolt, 300 millivolt, 400 millivolt, something like that. And if you have a noise of 100 millivolt or 150 millivolt for cycle to cycle, right, then it's becoming very critical, and sometimes it may give the RX wrong understanding also. Right. So because of that reason, you chop it and form as eye diagram and see the width of this, how much it is, right? How much is width, compared to the whole height, right? We may have to understand. So this in this angle, in the vertical way, right? How much you have empty space here, how much it is occupied in the low level, how much it is occupied in the high level, all those things, right? Part of the noise, right? So you can broadly classify into two parameters. One is like vertical way, how you are measuring, right? All those belongs to amplitude and noise. And horizontal way, whatever you are measuring, it's all related to timing or jitter in a broad classification. If you take a portion of the eye, see like the voltage, the 1 level and 0 level. Right? I'm not going to discuss about each formula or something, but vaguely, right? You may be chopping the different cycles and then overlaying as the eye diagram, and then in the center of the eye, you may have to take some 20% data and see like how much it is varying, right? And then this is the 1 level, meaning this is getting the high level, right? Mean of central 20% data in the upper eye. So this 20%, based on this 20% data, you will get some level, right? Some average level. That is what we call 1 level. Right? Similarly, the 0, this one, right? We will take it the 20% data in the center and then take some histogram, and then that will be called 0 level. Right? Just to get to know this, right? You not to be worried about the mathematics behind this, but at least you want to appreciate that 1 level, 0 level, all is like in the vertical scale you want to measure. Okay, same way, there is some parameter called deterministic noise. Right? There is a term called top deterministic noise and the base deterministic noise. You may be interested to know like how much the width of this from the 0 level and 1 level. Right? So from this place to this place, I hope you are able to see my cursor. Right? From this place to this place, right? Whatever the width, you may be interested to know, right? So that you can assure that it is not varying too much. So this parameter is like top deterministic noise. The top means nothing but the 1 level, right? The base means like the 0 level. Okay. And few more parameters called as eye height and eye width, right? Eye height is something like you want to know like what is this height, difference between this level and this level, right? In a different way. The formula is given for that is 1 level minus 3 sigma minus of 0 level plus 3 sigma, meaning like the 0 level plus 3 sigma somewhere here, right? The 1 level minus 3 sigma will come somewhere like this. This height somewhere here to here is the eye height, right? So this will give you like what is the allowance that you have right? In a layman term for the AT, we set it like VOL limit in the comparator. If you know, like generally we set it like 1.55, 1.75. We did it by 2, right? Which is for a 3.3 volt, you will make it like 3.3 divided by 2 plus 100 millivolt minus 100 millivolt, right? For the comparator setup. So to know that how much allowance you have to set this comparators, right, inside the RX, know like what is the I height. Okay, so indirectly it will educate you like what is the I height, right, for the RX performance or setup with the ATE. Okay, so there is one more parameter called I width, right? If it is so jittery, this in between gap will come reduce more and more. If it is less jitter, this in between gap will be more. So this phenomena is measured through the I width. Okay, so these are the common parameters. You might have heard about the I. One more important parameter is the crossing percentage, right? Exactly the crossing percent, ideal crossing percentage should be in the 50% of this whole height. Only then we can tell that P and N, the differential pair P and N are low to high level, right? Are balanced between each other, right? Otherwise, it will be one way, it will be inclined, so which is not good, and it will have different impact in different places. So for this to understand, we have a parameter called crossing percentage. This is also one of the important parameters in the I diagram. Okay, and there's one more, this one called I amplitude. You want to note it down that there's I amplitude and I height are different. Right? It is giving different parameter. The math behind that are different, but meant for different reasons. Right? That also you want to be aware that you are getting this. Okay, signal to noise ratio. Why we have to know the signal to noise ratio? The analog people may be talking about signal to noise ratio in a different way, but here is slightly different, right? Compared to this whole height, right? What is this height? That is what logically we have to see, because this height is too much compared to the whole height, then it's going to reduce the performance of the RX. Okay, so that is what signal to noise ratio. You may have to understand, okay, your noise width compared to the whole amplitude, what is that? Understand that this view. So this is given by the formula in the bottom. I will not explain too much about the formula because it very well can see in the website itself. Okay, there's something called RMS also. This is very common. Okay, I may be rushing a little bit here. Okay, but these two are one more important parameter: vertical eye closure and mask margin. Right? How this is important, right? Always, like any given standard will have something like a mask inside the eye. Right? They will particularly tell like, okay, this kind of mask should be used. Mask meaning, right? Any transition should not happen in this area. Any transition should not happen in this area. This is what, right? This rise time, fall time, and all those things, right, should be out of this area. So each standard is given by the master, right? Based on the standard that the committee that is coming up with the standard will tell that, right, what is a mask, and then no transition should come in the mask, and whatever the whatever the mask margin. Sorry. So mask, you have how big you have margin is. This gap you have will tell you that what is the mask margin that you have. And as you have more and more this area, you are very comfortable to operate on the RX side. Okay. So this how using the eye diagram, we will be measuring this area. The dotted lines to this area. What is the area of this? That is what we call as mask margin. Is one of the important, very important tests in the eye diagram, right? There is vertical eye closure also is there. Vertical eye closure is something like, if you just see in our layman terminology, how much you are closing the eye and then seeing, right? If you just visualize, if there is a sunlight, you will slowly close your eyes, this one, and then see the sun. No, you will not be blinking your eyes and then seeing. So how much you are closing your eyes, right, and then seeing the sun. No, that kind of closure measure is the vertical eye closure. How much you are closing, right? If you close more and more, you are not in the good position. Right? That is what the indirectly this parameter tells. So basically what we are trying to say is there are a lot of parameters in the IE and each one give parameters of the TX output waveform in a different angle. That's what you want to tell. And the parameters list, even though it's same for a different standard, it will be a different number. And also you can see even the formulas also may not be common across standards. Here and there, some kind of variation you will see in this one. Okay. To summarize, right? These are some of the parameters we have. This one, the 1 level, 0 level, top level. You may be thinking like almost everything is same. Right? What is the difference? Right? You can see like the formula you see, no, the 40 per top level and base level is 40%, whereas the 1 level is a 20% data in the center, right? And amplitude is 1 level minus 0 level, and voltage amplitude is top level to base level, right? They are seeing like so many parameters, but definitely believe me that each one has its own importance. Right. So, but some standard may have some parameters, some standard may not have some standard parameters. That is very common. It based on the criticality required for those parameters. Okay. This is all about the I parameters. The summary, right? We in the I parameters, these are the important parameters. We measure the jitter, the amplitude, the rise time, fall time, eye height, eye width, eye amplitude, crossing percentage, right? 0 level, 1 level, vertical eye, right? There are so many parameters we can measure from the eye diagram, right? It is like too much to really, all right? So this is about the eye diagram. I don't know whether Gauri, do so far any queries? Last time did we get any score from?
Yeah, we have a couple of questions.
Couple of questions. Okay, we'll be happy to answer.
One is on jitter from Hemant Kumar. If silicon designer says we need jitter-free clock for one of the high-speed interface and allowed jitter is less than 0.5 picosecond, what does that mean? Why he refers term jitter-free clock?
If you don't mind, can you repeat?
Sure. If the silicon designer says we need jitter-free clock for one of the high-speed interface and allowed jitter is less than 0.5 picoseconds, what does that mean? Why he refers to the jitter-free clock?
Actually, it's nothing like jitter-free clock, right? Because it's impossible to get a jitter-free clock, right? Maybe it's it can be called as very accurate clock, right? Accurate clock because like it's very qualitative, no? If you tell like okay, in the 10 years before, whatever we are telling, like it's very last time we talked about in the nanosecond range. Now we are talking about the picosecond range, right? In the future, we are going to talk about the femtosecond range. Already people started talking about this one. But anyway, what you are telling jitter-free clock and then less than 0.5 picoseconds is, right? The clock that is given as a source for your transmitter or for the receiver, right? Receiver generally the clock is not given. I don't know what is the scenario that you are talking about, but anyway, jitter-free clock. If you are claiming less than 0.5 picoseconds, the clock that is used as a reference clock in the TX should be less than the 0.5 picoseconds so that it will not have a big impact on your TX output data jitter. I don't know whether Hemant Kumar are able to, you can feel free to tell your comment.
Yeah, so I think that answers the basic question, but here how he came up with this zero point 0.5 picosecond, I mean whether he was able to simulate it and say that my silicon will work only if I provide the clock which has a jitter less than the zero point 0.5 picoseconds, or I mean what that how that number came into picture here.
Okay, good question. But you can back calculate what it means. Like always, we want to go with some standard, right? RX, right? The standard tells like RX will be able to work for until this jitter, right? First, that is what the standard comes from. If you are defining, the standard is defining that the RX supposed to work with 1 nanosecond or some hundred picoseconds jitter, right? And then the TX, right, supposed to give within that jitter, right? Much more than that, right? Because that line also will have some jitter, no? So it is driven back calculated from the RX tolerance, jitter tolerance. The RX has some 100 picoseconds tolerance, right? Then definitely the TX jitter, the TX data, the jitter is allowed, may not be 100 picoseconds, should be somewhere like 50 or 75 picoseconds, right? And in the TX, each one will have some contribution. Clock will have contribution, data will have some contribution, right? So the clock contribution, what it is, like that is the memory. This is what the clock maximum jitter that you can insert to your clock is this much, right? And then the data dependent jitter is this much. Something like each one will have budget, no share. Based on that only, they are telling that. This is a back calculated. Yes, these all are being simulated in the design stage.
Okay, yeah. So the simulated values are only till the PLL input. Like as you said, it's a reference clock to the PLL, and the PLL is able to generate the whatever is the high speed interface. Let's say PCI. So till the PLL input, we are able to control it using the simulation, right?
No, actually, generally in the simulation environment, right, PLL will be generally a mathematical model. Okay. They will add it like this jitter and then do the simulation.
Okay.
Generally, this PLL in the simulation model, design model, this one, right, it's a mathematical model. They will add it, they might have done with the 0.5 picosecond jitter in the PLL. So you are supposed to give this clock to the PLL or to PLL output, right? Whatever it is. I don't know what is that they have mentioned. Either it may be an input to the PLL, the clock input to the PLL, they may have defined that. You want to make sure that your clock to the PLL should be less than this jitter, right? Based on that, their PLL they might have characterized, right, for this particular jitter, in turn to have the share of PLL in the TX path.
Okay. Yeah. So understood. Yeah. So this is the simulated value and has to be within that range. Without that, you will not get the expected result on, let's say, eye diagram, or let's say
Yeah. You may not. You may get. You may not get, because like each one has its own budget, right? But your clock is like this, and whereas the other lanes and everything is very good, then you may be taking more share, whereas the others will not take more share. Right. There is a chance, but to make sure that you have a clean eye, definitely you want to limit it. Especially the clock circuit is one of the core thing.
Yeah. Thanks, Jagdish.
Yeah. What is the next question? Yeah. Go ahead, Lori.
Yes. The next question is, if the eye mask is within the limit, can we tell the height, width, and some more horizontal and vertical measurements are well within the margin? This is from Prabhu Natarajan.
Yeah, definitely. Right. We are telling that, okay, as I quoted, right, like everyone want to measure all the parameters. Eye mask is an indirect test, right? Eye mask margin is an indirect test to tell that indirectly, like the eye height, eye width, right? Those things can be indirectly guaranteed
That's a functional test.
as a functional test. Okay, so yes, you are right that eye mask can replace eye height and eye width. Hope that is answering. Prabhu?
Yeah.
Okay, so what is the next question?
Yeah. One more question from Venkatesh Mupatti.
Okay.
Any other special parameter tested for differential eye measurements or same as single-ended eye parameter? Is it recommended to plot the differential pair separately or individually?
Recommended to plot differentials separately. No. Generally, right, most of the recent HSIOs, right, I don't remember seeing some HSIO without differential pair. But in fact, this morning we were debating on this with a few people, right? This question, like I diagram can be plotted for single unit and differential pair logically. But I have seen like everywhere it is differential pair only we have made the I diagram. And I feel like all the parameters should be applicable for the single unit and differential pair, but the numbers may be different. Okay, so how you call it as VOL, VOH, you call it as VOD in the differential pair, but most of the interfaces, high-speed interface, you use differential pair only. Most of them, right? There is some exception, most of them, right? So, but according to me, right, I don't know, I have not seen any single unit I diagram, but according to me, should be same. It's possible to plot I diagram for both the differential pair and single unit and then do other parameters for both I diagrams in the same name, but numbers will be different. Okay, what else? Gauri, anything else?
That's it.
Okay, good. Happy to answer all the queries. Okay, so one more terminology, right? It's like a bathtub. I don't know whether you are able to see.
That is English.
Changing, huh?
Yeah, changing.
Yeah,
Okay.
we're able to see.
Okay, so the next terminology is a bathtub, right? So if you remember the TX setup that I have showed before, no, we were showing two different setup. That is the intention of showing two different setup, right? The TX output is connected to the DSO and the board, right? The board can do the functional kind of testing, and DSO can do the parametric kind of testing. Okay, so in the functional way of testing, in the AT environment, we maybe most of us may be knowing something like especially the Qualcomm team may be knowing about the walking strobe and all those times, right? We used to do a lot of care in the IO care, the low speed care and all, like a lot of walking strobe methods are being used in the SPA kind of interfaces, right? And the Qualcomm, right? So this kind of functional method, right, is one aspect, and another one is the parametric measurements. So whatever we so far discussed on the I side, right, you want to have some oscilloscope or the digitizer to measure the I diagram. In case you don't have the DSO or the, right, in the AT environment, right, you may have to go for different methodology to measure the parameters, which is called as functional method. That functional method, using functional method, how to measure the sum of the parameter is like one of the terminology is bathtub testing. Okay, so what is bathtub? From where it coming from? Right? Just recollect the setup that we have discussed, the TX setup, RX setup diagrams. Right? So you want to recollect and then tell you want to map it to that. One is like functional way of testing. One is like parametric way of testing. Parametric way of testing is the I diagram. Functional way of testing is the bathtub. Okay. So bathtub, how it came from? No, generally bathtub curve is mentioned in the reliability testing. Okay, I'm not going to discuss too much on this bathtub on the reliability side, right? We will go into the other one, but the reliability side, how they will use the bathtub is, right, to understand over time what is the failure rate. In the reliability, they will use the bathtub to the great extent. If you buy some ICs, in the early time, right, the failures will be more and more, very high, and then it will come down and down. And after a period, right, it will go down, and then once after some time, it will raise it. Okay, so that's what it is. Okay, so what is the bathtub in our terminology, right? We will discuss now. So this bathtub is bathtub curve in the side. So bathtub in our contest is like we have two bathtub curve. One is like the BR, the bit error ratio versus the time, right? People maybe what is zero here, right? Zero, if you remember, the center of the eye we call it as zero. Let's recollect that. Like if anyone not understanding, raise a question here, raise hand. I'll be happy to tell once again, right? The center of the eye we call it as zero, right? If you put the press mark on the center, we call it as zero. After that, right, the left side if you move like this side, and then this side, right side if you move like this, right? Just recall that the walking strobe method that we use in the ATE. The same way, if you use the vertical line strobing in the functional method, right? You will see if you move the vertical strobe line in the left side, you will start seeing more errors and more errors, right? In the bit error rate, right? And then you will the errors will increase like this. At the same time, from the eye center, if you move right side also your strobing point, you just imagine the strobing point for a given cycle in the AT environment. Right? Let's say you strobe a clock and you will strobe in the center of the clock, right? And if you move the strobe point in the right side and left side, you will start over a period, you will start seeing more failures in a pattern. The same thing is happening here. You assume that walking strobe pattern, right? Walking strobe with the pattern running in the for loop, and this is like the bit error versus the walking strobe. Okay, so this is what the timing bathtub. If you make the variation in the vertical line strobing place, they what the edge placement. Right? In the AE terminology, edge placement, the edge of the timing, right? If you vary from center to right side or left side, you will see more and more errors in the pattern. The same thing is happening here in the bathtub. Okay. Similarly, you can draw instead of walking strobe, you can change the comparator level, VOL and VOH level. Also, you can change and do it right in the center of the eye. It is called as zero. For example, in our case, right in the AT environment, what we call as zero is VDD by 2 is the zero. Right. After that, if you move up and down, right, it is something left side and right side. From the eye center, right side to that some 20 millio, left side to that. Not right side, up 20 millio, down 20 millio, something like that, right? If you move up and down, right, the strobing point, basically the compass setup of the VOL VOH in our AT terminology. If you move, then you will see more and more errors. So these two things, right, the equivalent one is called as bathtub in the HSIO space. Okay. If you don't mind, everyone can tell that, okay, yes, you understand or no understand within a few seconds. We like to see this one, the acknowledgement from most of you. Are we getting? Sorry?
Yeah, I didn't get the polling, sir. Yeah, I'm started getting.
Yeah,
I have one more question from George. Can you take timing and voltage parameter to explain this?
Timing and voltage parameters to explain this. Is it George Philip?
Yes. Yes.
Can you explain the question better, George, if you don't mind?
Yeah, Jagdish, what I am trying to ask is, can you take a parameter, like for example, for the voltage case, VOH as an example, right? VOH, how we will use this voltage bathtub to measure the VOH? That parameter, how will you measure it? With the parameter, if you can explain, it will be easy to understand.
Okay, but I will make it straightforward. I will tell a different way, right? Let's say I will do one more time. Okay, let me attempt one more time, and then you can answer whether it's giving the answer or not, right? Anyway, feel free to tell how many times you want to repeat in a different way. I will be happy to repeat, not a problem, right? In a pattern test, let's say I'm running a pattern in our ATE environment. Okay. and then I want to find out the VOL, VOH. Right. Using a functional pattern, not using the PPM view. Okay. I am going to vary the VOH level and VOL level on the comparator and run the pattern again and again. Okay. So what I will do is like, okay, initially I will take it like, okay, the VDD by 2, right? If it is 3.3, 3.3 by 2 is 6.5. So I set like 1.6 as the voltage in the VOL comparator. VOH comparator, I will set it like 1.7. Okay, and then I run the pattern. It is giving 0 error. Right? It is giving 0 error. So far it's clear?
Error comes 0.
Right. When you run the pattern, it is giving 0 error. And slowly what I am doing is moving up the VOH setting. Instead of 1.7, I am making 1.75, 1.85, 1.95. And over a period at 2.2 volt or something, 2.3 volt or 2.4 volt, I may get only one error. Right? VOH 2.4, VOL 1 volt. Right? I may get one error. Right? As I move up and towards VDD and ground, the VOH towards VDD and VOL towards the ground, I may see more errors. Right. So the same thing if you correlate here, 0 is like VDD by 2. Right. And this is given in the not the number of failures, bit error ratio, meaning the bit error ratio is nothing but the ratio between the number of bits transmitted versus number of errors. That's why 1 to e to the power 15 means you are sending 10 to the power 15 10 to the power 15 bits in the pattern, and then you are not getting any error. Then this is corresponding to this place. And once you start seeing some error, this is like little bit the error is increasing. So in this place there is no error. Right, and moving the voltage VOL and VOH here and there, right, widening little bit here and there, right, it is not having the error. But once you reach the VOL, VOH like little bit more and more, opening up the width more and more, right, you will start seeing the errors. So that maybe you can tell like, okay, are you able to appreciate now or no? Maybe otherwise I will use my board to tell you. Judge?
Yeah, so in this picture, we are seeing that 40.3 millivolt, which means 20 on the right side and 20 on the left side. So are you saying that VOH will be the mid value plus 20 millivolt or something like that?
Yes, yes. It is like VOD. In this case, it is not VOL, VOH. It is in the case VOD is 40.3. For 40.3, there is no error in the functional pattern. After that, if you increase a bit more, the error also increasing. Over a period, it is like giving so much error. That is what it is. So, at which here, no one, if it reaches here, right, it means to tell that, okay, it is fully failing. This place. All the bits in the pattern are failing. All the compares are failing. This is what the point here. Okay. So similarly here, no, in this place, the strobe is in the center. In the ATE space, we call it as the cycle starting point 0. No, you don't take it that way. You make this 0 point cycle by 2. If your cycle is 10 nanosecond and 5 nanosecond is 0 nanosecond here. After that, if you move the stroke towards the initial cycle, then left side. Towards the right side, it is this one. So you make it like it's a full cycle like this, and center of the cycle is this 0. Same way, you are measuring the error by moving the edge. Here, edge alone you are moving. Here, you are making the comparator setting widening. Okay, anyone of you, anyone of others also, if you don't understand, feel free to ask. Nothing wrong, right? We are not here to rush and then getting things done. Okay. Otherwise, George, are you okay now or not? Okay. Yeah, you can rethink. I will appreciate, like, we are not going to rush here. Tomorrow also you can raise questions, right? You upfront you can send all the queries that you have to Gauri, and then we'll be happy to answer the queries before the starting of tomorrow session. The disclaimer is that, okay, I am not an expert in HSIO. Okay, we will try to answer you whatever with the limited knowledge that we have gained, right, in the past few months, right? We are doing a lot of homework in the HSIO space, right? And then we are also learners, but compared to most of you, maybe we are a bit ahead, right? That's why we could communicate all this terminologies to you, right? But definitely we are not experts or something where we will be in a position to answer all your queries, right? We will be happy to hear all your queries. We will answer what are the best that we can do, and we'll be happy to do some of the for queries. We will be happy to do homework for your queries, right? Not immediately. Definitely, we can get back to you also on the queries later point of time also. But feel free to queries related to this topic, right? That's more important. Okay. So horizontal bathtub, right? As I explained you, it is like horizontal bathtub used to find out, like, it's indirectly, right? It will help us to find out the deterministic jitter and random jitter. Right? We are still doing that homework, but we are not very clear on this so far. Right? We can attack in a different time, right? Okay. How the can be interpreted for the deterministic and random jitter? As of now, we are not clear. Okay, but you take the message that deterministic jitter and random jitter classification can be done using the bathtub. That message at least you can get from here. Okay. And through the vertical bathtub, right, you can get all this data. It's in a different way it is quoted, right? The high level standard deviation, low level standard deviation, peak to peak noise, all those things. The same like eye diagram here also you can do, but please understand or visualize that in the eye diagram, right, we are chopping the real waveform and then again overlaying, right? It's at the real time. Whereas in this one, you are using a functional test to do a for loop, same like walking stop in the ATE. You are doing running a pattern again and again, right? And then making sure you are getting that data. So that is like very time consuming. So bathtub test also very time consuming compared to the eye diagram. But you can get similar data here also, right? It's a different form it is given, right? The bathtub, same thing, right? If you charge it the same waveform, it is given in the vertical scale here. Okay. So another this thing like to tell like, okay, initial time it is because of the random jitter, and then the over a period, if you go left side and right side in the eye diagram, it is a deterministic jitter. So bathtub can give this kind of information for you. And it is collected using the bird, not through the oscilloscope. But some oscilloscope also facilitated the doing the bathtub. That is also there, right? There is some software to do that also. But in general, bathtub can be done using the bird or the ATE functional test. Either one can be used for this kind of thing. Okay. So coming to the BR, just once again I want to tell that, okay, the BR. What is BER is, like, so far we have discussed the BER so many times. BER is like bit error rate or bit error ratio. Right? Bit error ratio is the number of errors compared to the total number transmitted. Right? You want to always compare the total number of bits compared to that, how many errors you are getting. That is what bit error ratio. And that is generally done using this diagram. Right? This the logic diagram is like, you will have a bird transmitter and you will have a dot, right? And then that is a loop back, and you recollect that whatever TX RX loop back earlier I showed, right? That TX, here is a dot TX, here is a dot RX, right? And that will be given to the bird receiver, right? With this kind of setup only BER is done, right? With this setup, right, the BR can be measured, or the bathtub also can be measured using this setup. That is what we are trying to tell here. Okay. And what are the factors that are affecting the BR is the interference, and then the increased transmitted power, reduced bandwidth, all those things. Anyway, this all may not be so meaningful now. It will be more meaningful as we move along this session. Okay, so one of the from the beginning I was telling like eye counter, right? Eye counter is a new, maybe most of them, maybe new for the most of the people here, right? Eye counter is bit different compared to the eye diagram. Okay, and this eye counter is also similar like walking stroke. It's a nested for loop, right? Even the Qualcomm kind of environment, we are doing this kind of walking stroke versus the
Jagdish,
yeah.
Prasad, so this bit error, we are just checking the performance of the receiver.
Bit error, yes. It can be bit error rate, right? It can be both. If you remember the 3 setups I have showed now, bit error rate, you can measure the performance at TX, right? Through loop back.
Okay.
Right? If it is loop back, you are measuring the bit error rate for the RX combination of RX and DX.
Okay.
Right, but if you are using only the RX, if there's error detector is in your DAT, then you are measuring only the bit error rate of RX. Do you want me to go to the setup diagram? I can go to the setup diagram.
Got it.
Okay, so bit error rate can be measured for the TX and can be measured for the RX. So if you are using the bird tester connecting to the RX, then we are measuring the bit error rate of the RX. If you have the error detector in the RX of the DAT.
Okay.
Right, if you are doing the loop back, you are doing the bit error rate in the combination of RX and TX. Okay, and sometimes you can just connect the TX alone to the bit error rate tester and educate that to the bit error rate tester, right, bird, that this kind of pattern only this TX is giving. So because there will be some PRBS generated in the DAT, right, and tells that this is a PRBS 31 or PRBS 15 or something. PRBS, this kind of bit stream will be pumped out from the TX, right? That time, right, the bird, you will educate both the bird and the device that, okay, this kind of pattern only you want to send and this kind of pattern only you will receive. This, anyway, I will discuss tomorrow in the PRBS section, how this PRBS is selected, what number and all those things, right? Okay. For now, it is like there is a 3 kind of setup: the bird and RTX loopback, bird for TX, bird for the RX.
Okay.
Okay, 3 kind of setup. Okay, so that's what bird. Okay, eye counter, no. Okay, if you remember, I was telling, right, if you want to measure the eye diagram, right, you want to use the DSO. If you want to use the bathtub or the BR testing, you want to use the BERT tester. Okay, BERT is a functional tester, DSO is the parametric tester. Okay, but sometime, right, not sometime, most of the HSIO nowadays, right, is very difficult to connect 2 instruments. Right, you want to have a relay or some other circuit like bias T circuit, we call bias T circuit, or the RF switch. Those kind of things to be introduced to connect to 2 different instruments, which is like very painful in the HSIO space, right? So you may have to do something like an eye diagram, right, in the board, using the board itself or using the functional test itself, right? With the Qualcomm also, no, most of the time we will not measure the timing, no, we will use the walking stroke to measure, right? So, but I told like walking stroke is something like a bathtub. Then once again, what is the eye counter, right? So here is a small change in the walking stroke. After seeing this, I was wondering why the Qualcomm is doing walking stroke all the way. They can use something like an eye counter. This is a very good pointer for you people to think about this actually. What is this one? No, In the walking strobe, right? If you are just strobing only the timing, you will vary the edge, right? If you want to strobe edge and the edges, then you want to have a nested for loop. I don't know how many of you can follow up me. Maybe otherwise feel free to stop me. Okay. If I want to measure the edge and the voltage, right, as a bathtub, then what I want to do? In the bathtub, I will have one for loop for timing, one for loop for voltage. These are two different for loop for the bathtub, right? Whereas if I want to do two-dimensional, for every vertical stroke point, I should see like what is the voltages. That is what indirectly I diagram, right? Or maybe mask, right? If I have a nested for loop, right? One for loop for the timing variation and inner for loop for the voltage variation, or vice versa, right? Then I can do the eye diagram kind of thing. Whereas this eye contour, right, it uses something like angular direction. That is what is a very important point to note down. It is not pure for nested for loop, right? It will like here, right? If I do the nested for loop, I will have this data the point here. Slowly I will move here in this way, right? And then I move this point here and then move like this, right? Likewise, next point like this, like next point like this, right? Like this nested loop below. But you see, right, this area, right, mostly you will not have any problem, right? You will see problem only in this boundary, right? So why should I for loop, nested for loop use these areas? It's not really required, no? So what we will use, like instead of nested for loop, right, we use some angular algorithm to strobe like this. So my instead of nested for loop, my data points will be moving in the angular way, right, to make sure that you don't have error, and then it will be less time you can do. If you use nested for loop, it will be so many points, right? So it's something like a angular approach you will do, the strobe points. The for loop, instead of nested for loop, you will have angular loop, right? Angular loop, and then it's like data points can be reduced, but still whatever you can achieve in the eye diagram, same thing you can achieve. More than the eye diagram, this can be, right, when you do the for loop for the walking strobe in the ATE, you look for zero error. Okay, so you look for zero error, whereas in this tell that okay, I am okay for 10 errors, 5 15 errors, something like that, right? You can tell that scenario or plot it. When you run this one, no pattern, you don't look for path, look for the number of errors. One is like going in the, and another one is plotting the error numbers. Not in the walking strobe, always plot for zero error. But here we will plot for the number of errors. So I only find out like, okay, if I move here, right, how many errors you are getting. So with given number of errors, what will be the outer boundary? You will be able to tell. This kind of scenario you cannot even measure in the eye diagram. So what I'm trying to say is, this is like in one aspect is a superset of eye diagram, but it is very time consuming, right? But it is better. The for loop is better than the walking strobe. This one, this is the angular approach, right? I don't know how many of you understood. Maybe here I want to stop and wait for a few minutes for your voting, polling. Right? Feel free to vote. I can listen from people. Because it's a very important point. Right? Eye contour is like very new terminology, maybe new terminology for most of you. And it's a very good technique, can be utilized in the AT also. Polling. Gauri, open up the polling and then maybe we watch.
Sure. We have a question.
Yes, Gauri. Yes, Gauri, what is the question? Gauri? Are you there?
Can't you use PMU digitizer in digital instrument for this parametric test? Is it due to limited sampling rate of the digitizer? We use functional method.
The answer is yes and no, right? If you remember, right, we are talking about the high speed, right? We are talking about 5 gigabits per second, 8 gigabits per second, 10 gigabits per second, right? The PCIe now, whatever the Qualcomm people may be doing the PCIe at the 16 gigabits per second, right? In that aspect, right, it's not straightforward to use the digitizer, right? But there are some digitizers, right? And with the undersampling method, right, we can do the eye diagram. Yes, you are right. Right. That also we are going to discuss in the future classes on Thursday or something on this aspect. But the straightforward answer is right. The digitizer directly cannot measure do the eye diagram for the current HSIO. This one, the interfaces. But it is possible with the interface. But what we are talking about in this eye counter is there is a digitizer. The eye counter is used using the functional testing alone. If you don't have the DSO or the digitizer at high speed, right, you may have to use the functional testing itself, right, to do this one. Right. In this case, eye counter is named in the BERT tester. In the BERT, using the BERT tester, how to do something equivalent to the eye diagram, right? And also eye diagram, right, will not tell you like for a given error rate, what is the eye diagram will look like. Whereas in this one, right, for a given BR rate, what the eye diagram will look like, the boundary. That's what you can see, right, in the top circles, right? The one circle with a different bit rate, another circle with one more bit rate, and third circle with another bit rate. Okay. So who was answering that, asking this question? Maybe they can answer. Is that anything is convincing to them or not?
This is from George.
Okay, George Philip.
Yes, Jagdish, again, one more question in this angle is this eye condor test, is it a characteristic in the AT environment? Is it in the production type of test or a characteristics type?
Okay, most probably it is like the this eye counter, actually the terminology is from the bench environment, right? But if you do the same thing in your AT environment, using the functional testing, that is also called as eye counter, right? Eye counter, right? When you call it eye counter, when you call as bathtub, right? If you are using functional testing method with one for loop, then it should be called as bathtub. If you are using nested for loop, right, it's almost like an eye diagram. If you are using angular, this one with a given bit rate, then it is called as eye counter. So small difference only is there, but it has a lot of importance, and it can give different view of your TX output or RX. Okay, the polling has been done, Gauri. How is the polling?
There is no polling, sir. One question was there.
No, polling, why people are not interested to tell. Right? You need to understand fully, at least you appreciate that, right? Eye diagram is, I will repeat, at least if you understand this is good here, right? You can penetrate later, because in to be frank, right, we were trying to understand all these concepts for last 5 to 6 months, right? It is impossible for you to visualize and understand in a single day. Okay, that I agree, right? But at least in the top level, eye diagram is done using the oscilloscope or using the digitizer, right? And you will see this rise time, fall time, eye width, and all those things. Bathtub is using the functional tester, right? for example, in our ATE environment, you use a comparator, not the digitizer. Comparator logic you use for the bathtub. And the counter also you use the same comparator, but in the bathtub is only one for loop. Either it is a timing for loop or the voltage for loop in the PE card with the comparator. You equate to that. And whereas in the I counter way, you want to have a nested for loop with skipping points in the angular way. That is one thing. This angular way, right? Angular way you want to do. It is not straightforward nested loop, because if you do the nested loop for straightforward, it will take enormous time, right? Running a pattern again. So it's an angular way of doing the nested loop, and with some of the number defined, right? You when you are doing the this one, no, you will plot the error number also pattern, right? In an AT environment, look for the zero error. You do the walking stone. Here you look for the number of errors in the pattern. So number of errors with the angular for loop using the functional method is the I counter. Who don't know, like how many of right? How many we got the scoring less than 5?
No, no one has responded.
No one has responded. Then everyone's 0. Maybe then we have to pull some people. Right, Prasad, can you pull one of your team member and then comment on this?
Yeah, let me check.
Feel free to tell, right? I don't expect that everyone should understand, right? But it's at least tell, okay, you don't understand. I'll attempt in a different way. You can nominate Prasad. Person.
Yeah, Anirudh, do you have anything? Okay.
No, I was asking, okay, can you ask some of your team member to comment, able to summarize like I diagram versus bathtub versus I counter, top level, or maybe I'll complete the I counter and then I'll take it. Maybe please be prepared to summarize, right? We like to get some summary from 2 or 3 people in this angle. I diagram versus bathtub versus I counter. This is a question, open question, right? Okay. So you see, right, the I diagram versus I counter, right? I diagram will look like this, right? And then I counter also will look like this. Nothing different, right? But I diagram, right, will not contain the bit error rate in it. Whereas here, right, this will have the information about, right, the error rate. With the given error rate, how the I diagram look like. Okay, this is what the message that you want to get, right, in this, right, I diagram versus I counter. So you see, right, you can see like this is a BR counter, right? I counter is used using the B as a reference and using the BERT tester, whereas I diagram is used in the oscilloscope. Okay, this is the oscilloscope, this is done in the BERT tester, right? This taking the ADC samples, right? In the use like something like a digitizer in the tester. Here it is like pinner reference card in the tester, equivalent to that. Okay, to summarize the I and then I counter, you can see like the chopped data samples of each cycle are overlapped over each other to form I width with respect to 1 unit interval. That's what I was telling again. The chopped data samples of each cycle, right? It should be more than a cycle. It's not like each cycle, more than a cycle. Here, decision point is fixed first, and then it is moved in all direction, right? It's the center on this one, right? That's what angular approach I was telling. When it's past that BR, right? For a given BR, right, you can move it, or it is like as you move, register the bit error rate. Okay, something like the I counter. BR is behind the I counter, whereas here is no. Okay, this uses the EC, here uses the pinner reference card kind of comparator logic. Okay, It uses a repeater rate tester. It uses a sampling oscilloscope. With all combination monitors, it becomes easy to see when rise time are too slow, right? Here, right, you can see a lot of parameters like jitter and other things, whereas here it is not so easy to see the jitter kind of parameters, right? It is like very qualitative information. It is quantitative. In the name of, I will not fully into this line, but this is a quantitative information for each parameter, but not on the BR side. But indirectly, you can tell qualitatively how the BR will look like based on this. But here you can tell physically how the BR will be for each contour. Okay, and diagram plotted with real-time oscilloscope are faster, right? You can correlate this particular line, right? If you are using the oversampling technique, the eye diagram will be very fast. Whereas the BR contour, if you use the functional method, like a comparator logic in the PE card, it will be very slow in the functional method. But there is one more technique called undersampling method, doing the eye diagram using undersampling method. Right nowadays, whatever the ATE instrument is using the undersampling method, not the oversampling method. Whereas the bench instruments using most of the bench instruments using the oversampling method. Right? So undersampling method, if you use it, it will be in between the eye contour and the this one. So if you take this line, you will know the test time angle. I will re-insist. Oversampling method using digitizer or using the real-time oscilloscope will have the best test time. Okay, the BR contour will have very poor test time, whereas the undersampling method for the eye diagram will have in between these two. That is what the message we want to tell here. Okay, just to give you, right, in the US 10G also the similar thing we can do, right? The it is like almost like they are using the bathtub and the eye contour, the techniques together, and they are doing the same way. That is what I just want to tie up. I'm not going to discuss about the US 10G here. Right? I don't know how many of you from the UFlex environment. US 10G ultra serial 10 gigabits per second instrument in the UFlex. Also doing this kind of techniques. If you ask me like why I want to know all those techniques, no. If you know that, okay, if you know that eye contour, bathtub and eye diagram concepts, you can very well map into the ATE and find out the pitfalls ATE has and even act accordingly. That is what the intention of telling this eye contour, bathtub and eye diagram. So if you see the ATE instruments also, all the three concepts are being used in a different instruments. Exactly. If you are very familiar with these three different concepts, right, you will be able to the other one. Okay, now once again I will ask the polling. Actually, there's only one more topic. And I'll look for the this one. Eye monitor. Okay. So there is one more technique called eye monitor. Right, you may be a bit late also to logically close. Right, there is something like eye diagram, eye contour, bathtub, all those things. Right, eye monitor is something like the eye monitor is not on the test side. Right, it is used in the receiver side. Right. Receiver, right, in the RX side, you will have some additional circuitry in the RX, right, to do similar thing like whatever in the bathtub we are doing, no? Bathtub, whatever we are doing, or eye contour, whatever we are doing, there is something called eye monitor, right? There is a special circuitry called eye monitor. It is not just eye monitor, it's an eye opening monitor, right? If you have nowadays, like in the earlier days, right, not earlier days, maybe the current scenarios in the HSIO, right? If you know that, okay, this is what the TA is going to give, right? And you can set up the RX accordingly, and then it will be, once it is set, it will be fine, right? That's why you want to measure the eye diagram, all those things. But in the recent one, the PAM4 kind of thing, you know, you want to monitor the eye diagram in a live, this one, in the application itself, you want to monitor the eye opening. Because based on the temperature, based on the other factors, right, over a period, your eye diagram may become poor. So you need some eye monitoring circuit in the RX to do continuous eye diagram measurement and decide to do some fine tuning in the RX circuitry, input circuitry. I will repeat. You can see this is the RX input. The data is RX input. There is a filter. We call it as this filter is an equalizer. Right? After equalizing, the data is taken and there is an eye monitor circuit is there. Right? This eye monitor will see like how good is this eye. Right? Using the functional method that you want to understand. Right? Using functional method. But there are in the RX there are two techniques. One is functional method technique. Functional method technique is something like using the comparator. So one more technique is called digitizer technique, which is using the ADC, right? I don't know whether I'm confusing a lot, right? Eye monitor circuit may have two different circuitry. One is ADC circuit, one is the comparator circuit. If it has comparator circuit, you map it to the bird. If it has ADC, you map it to the DSO, right? Either one it will have, and it will analyze and change the filter settings on the live, on the real application, so that the eye opening is becoming better and better, right? This is what happening in this RX chain. So eye monitor is nothing but a circuit inside the RX chain, right? To do similar work like eye counter or eye diagram and tune the filter. That is what the message. The filter will be looking like this. This will be tomorrow. We will explain on the equalizer part. How is this equalizer is done? What is this, all those things? As of now, we just assume that there is a equalizing filters are there, and this eye opening continuously monitored, and it is tuning the filter on the real time. Okay, this much I think the eye monitor is enough, right? Something like the same like eye counter, you'll see this diagram in the eye monitor also, right? So just for you to understand, right? We can even test the eye mask inside the chip in the RX using the eye monitor circuit. That is what it's showing, right? But you understand that, okay, eye monitor circuit can be of equivalent to this one. Eye monitor circuit can be equivalent to the DSO or the BERT. It depends on the circuit what is used, right? It's mainly used for the real-time application monitoring. But it will do the same stuff like a BERT or the DSO. You can use this circuit for the testing purpose. During testing, right, you can use this eye monitor circuit to the great extent, right, to do that. But the problem here, I will tell you, right, the challenge here is, right, how all those things, right, if you how to mimic in the AT setup, if you are testing in the ETX, that's all the challenge, right? We are not started about the challenge, right? I want to tell what is the terminologies used and all those things. We will then you will assume that, okay, what is the complexity you have in testing the adjusted IO, and then in terms multi-dimensional challenges in the PAM4, right? So I have not taken you to the PAM4 at all. Okay. Okay, so Prasad, maybe you can ask one of your best guy to summarize, so that I will take it as a master. This one, okay. What is the icon to write this one and this one? So can we try? Feel free to.
Yeah.
You can tell the truth first. Am I succeeded in making you understand the top level at least what is the difference between eye monitor, eye counter, path left, and eye diagram? The four different terminologies.
Yeah, I mean, there is a lot of echo. So these terminologies, right, kind of new, even though in Qualcomm we do all this eye diagram and some of the measurements and all, like beat, eye counter. These are some of the new terms what we are seeing, because ours is mostly kind of a DFT based, and where all the BIS takes care of it, and we don't do too much of CAR kind of efforts there. So yeah, this is kind of new, but whatever, at least whatever I grasp it, at least on a high level, I kind of got to some of these terms, what exactly it means, and then why we have to do and all. Maybe one of my DDR guys also joined. Maybe I'll ask. Anirudh, can you share some of your feedback?
Yeah, what you understood, what you didn't understand. That's what.
Yeah, sure. Yeah, sure, Prasad. So, yeah, Jagdish, yeah, first of all, thank you so much for this one. Yeah, obviously, as Prasad said, yes, we usually do all the basic things only in care. Like if you talk about this session, yes, the eye monitor is something that we do as a part of our care in Qualcomm. But when we talk about the other concepts like eye diagram and all, this is not something which we follow. On a top level, since you said you want me to summarize a bit whatever you have taught, so yeah, for iDram, what I have understood personally is it's like a a digital signal that can be like, okay, for from a receiver, how much it is repeatedly called. So that is something that we are checking again and again, and they are applying it to a vertical input. So it's like a repetitively what we are checking is what we call as eye diagram. Whereas when we talk about the bathtub, it's mainly related to the failure rate or the bit error rate that we check over here. So it's like there are three parts that you showed us using the dash diagram as well, and then over there we had a decreasing failure rate, and then in between we had a constant rate, and then at last we had an increasing failure rate. So that's the reason it was like in the form of a bat rate. I mean, please pitch in if I am somewhere I'm wrong over here.
So it's like a minimal error. Yeah, minimal error in the center. As we move the strobing point, you will have more errors. Or as you move the comparator voltage wider and wider, right, then it will become more errors. As like yeah.
Correct. So you mean to say like, okay, right from the starting, it will be like in the decreasing form. So that's why it's in the form over time. Then it becomes constant where it goes towards the lower range. And then it goes up, right? Is that correct?
If you make the voltage setting in the center, right, you will have minimal or zero error. Right.
Okay.
Let's say VDD by 2. If you make the VOL, VOH setup both very close to the VDD by 2, right, your error will be minimal. And if you make up the VOL, VOH wider and wider, right, the error will be more for the pattern.
Okay.
So same thing in the bathtub, right? We are moving the VOD more and more, right? And then the error will be, in fact, in the bathtub, it is like one side is shown. Like in the higher side, the VOH alone, if you show this one on the right side, it is. VOL means left side alone, right? You move basically you are moving the horizontal line, right, on the voltage scale, right, to see that error, how the error it is. If I vary the voltage, VOL, VOH compared to setting, how the error will look like. That is what one of the bathtub. And also another bathtub is like the strobing point, the timing strobing point, right? If you move it from the center of the cycle to this side, that side, how will be the error will be growing. Okay. So what you got about the eye quantum? If the bus is there, no, why we want to do the eye quantum?
Yeah, I mean, so far the understanding is, okay, again, it is actually a bit rate check at the boundaries. So there you have shown us 3 lines, but yeah, I mean, the difference between this, to be very frank, why we are going about counter and all this, something which is not clear at the moment.
Can you repeat, which is not clear?
The error eye counter actually. Yeah, obviously we have seen some kind of eye diagrams. I mean, the diagrams over there, which is like, okay, again, we have 3 kinds of, the checks at the boundaries. Okay. But yeah, why we are going for eye counter or something, that is, sorry, I'm not very clear with that.
No problem. Anyway, I will repeat here for everyone, right? In the diagram, right, we are just using the digitizer and sampling it and then putting the waveform. So there is no bit error involved there, right? Because anytime if you want to tell like the receiver, right, any standard does not tell that, okay, receiver should understand all the bits that is TX transmitting. We have an allowance that, okay, if I'm sending some 1 million bits, right, this many error can be faulty. Right, that's not bit error rate, right? For a given bit error rate, right, what should be my eye diagram? In the eye diagram, the bit error rate is not at all tied up. In the eye contour, we are telling like how the eye diagram will look like for a given BR rate. Accepting some failures, how the eye will look like. Because we are not looking for zero error. In LSIO, when you are using the walking strobe or this one, no, we always look for a zero error in the pattern. Right? But here I am telling like, hey, no, I don't want to zero error because in the application itself, I'm not looking for zero error. I can have, right, if I send 1 million bits, I can have some 10 bits error. So with 10 bits error, how the eye diagram will look like? For 100 bits error, how the eye diagram will look like? So eye contour will give that information.
Okay, got it.
So is it like some kind of a margin, Jagdish?
Yes.
Right.
For a given bit rate, how the eye diagram will look like? In the normal eye diagram, right, the bit error is not tied up. It does not expected. It is plotting only the waveform.
Okay. So based on this margin, we will tell, okay, how good is the performance and so on and so on.
Yeah, yeah. So for this bit error, how the eye diagram will look like. For the another bit error rate, how the eye diagram will look like. So that's why you have so many different this one. Okay. And one more thing I want to tell in the eye monitor, there is no bit error rate. Right? It is like MTR, mask error rate. Right? This is also one more variable. Anyway, I will not go in deep in this one. In the eye monitor, what it looks for is not the number of bits error. It will tell like it will create one mask in the eye and it will make sure that nothing is coming inside the mask. Eye mask, if you remember, right? Eye mask is a pattern given by a particular standard. So it will have the eye mask inside the device and it will make sure that all the data that is coming in the strobing point not falling inside the mask, right?
That is a dotted line what you highlighted, right? In the eye.
Yeah,
that is the mask, whatever the limit you have in that.
The mask, dotted lines, no, that's the mask given by the standard, right? So inside the mask, how many high and low is coming, no? That is the mask error rate.
Right.
Okay, that is what is done by the eye monitor. There is a small difference only, nothing great there. But anyway, definitely right. Last time I used to think like, okay, bench instrument is okay. Bench instrument, why should I understand that? No. But here, right, if you take the US 10G and US 60G and 9G, right, they are using different concepts, right? If you know eye diagram, bathtub, eye monitor, eye contour, this four, no, you can map it to any instrument in the ATE. Either they use the functional method or the undersampling method or the oversampling method. Okay. And this algorithms use, like, if you are familiar with these four methods, you can do anything in the ATE. You can understand any instrument in the ATE, and each one require different for loops, different method of testing. That's why if you want to be ATE engineer, you should, for the HSIO, you want to understand these four concepts, right? Anyway, I don't expect that you want to understand fully in this session or training, right? If you want, maybe if you put in the eye monitor or this one, or we will be happy to help you to zoom in any area. If you know this four different techniques, then you can penetrate there, zoom in there, or you can take help from people like us, right? Where we are a bit better than you. It's not like we are experts, a bit better than you, so that we can help to make it faster than you. That is what the message here.
Yeah, sure.
Okay, so yeah, any questions?
Yeah, just one more question. So in eye monitors and all, we have certain kind of specs that we come up, and those are based on all the frequencies that we have, the frequency of operation basically. So how do we take care of these margins and all those kind of things in eye counter actually?
How we take care the mask margin in the eye contour?
Yes.
That is very simple only, because like I mask whatever the standard defines, no, the same mask we want to take it, and with the given bit error rate by the standard. You want to take, there are so many circles in the eye contour, even though there are so many circles, you want to take a circle of corresponding your BR rate given by the standard, also your mask of the standard, because each standard has different mask pattern. So that mask should be overlaid in the eye contour and make sure that is ring, right, not following inside that mask.
So is it based on the process technology or is it based on the frequency?
That is done in the DSP, but while testing, right, it should be based on the standard. If it is a PCIe, if it is a whatever it is, no, the I mask is a standard. BR number also is given by the standard. We have to take it from the standard on the mask pattern. Mask pattern is given by the standard, so we have to take it the mask pattern and then put inside the I counter using the DSP.
Okay. Sorry, my question is based on that standard only. So how do we set that standard?
No, that is you and me cannot set the standard. No, PCIe Gen 4, Gen 3 means the PCIe SIG already given that this is the pattern you want to use. And these are the PR number you want to use. That is already predefined.
Okay, so it's based on generation, right? I mean, Gen 3, Gen 4.
Yeah. It is already in the this one standard.
All right, got it. Thanks.
From the standard, you want to process it using DSP with the raw error numbers in the I counter. Okay. So, Gauri, any other questions?
Yeah, one question from Prabhu Natarajan. Can we tell if I use a I monitor circuit, can I do the mask with BERT?
Can we tell?
If I use the I monitor circuit,
yeah.
Do I mask with BERT?
Okay. No, actually, it's not equivalent, right? Why it is, right? I monitor, right, will not take care of the BER, right? It will take only the mask pattern, meaning it will make sure that your data is not coming inside the mask. So it is the replacement for the mask margin test, right? But it will not test the BER directly. Indirectly, some way it can commit. It can guarantee, but directly it is not the replacement for BER test. Whereas in the BER BERT, even though you do the mask margin in the BERT using the I counter only can replace in the BERT, right? In the I counter mask you can make it, but that mask is will take care the BER, whereas here it is only take care that it is only the data is not coming inside the mask. Okay, for example, TX, right, supposed to send 110. Okay, for some or other reason it is send 101, right? The I counter will code it that as one error there. Okay, whereas the I monitor will not quote as an error there, because for it, right, it is 101 it is understood because it does not know the reference data. Because the live application, it does not know what is the data that is going to be coming from the TX. It's going to vary, right? So it can't be replacement for this one. I monitor can do mask test, but it is not the replacement of doing the mask test in the BERT, because in the BERT you will take care the BER also. Here it won't take care. That is what the answer. Is that clear, Prabhu? At least you got something. Okay.
Yeah, it is clear to me. I understand. It's only adjusting the mass with respect to the 1 and 0 not.
Yeah, there is a tiny difference between all these four. Right? It is not same.
Yeah.
Okay. So any other question, Gauri?
No other questions.
Okay. So actually we have some videos. So what we will do is, like, it's maybe too late, right? I don't want to extend anymore. We'll play the video tomorrow, right? From there we'll start. Okay. And feel free to in this, right? We will try to answer whatever possible, right? So see you tomorrow, right? With more questions, right? First half an hour we can spend in the video and the questions that we have in the course. Think through that, and then if you don't get the top level information, you can come through, right? So I know that it is not very easy for everyone to visualize everything, and we also were struggling to see like how not making the training too much days and then giving the information to you, no, before PAM4, right? Because our intention is not to teach you all those things. Our intention is to tell you like what is the PAM4 testing, right? So we want to give you all this information as a prerequisite. That is what the information. But it is good that people are also started understanding and some questions are coming. Okay. So with this prerequisite only, we should go to the PAM4. So we will work on the prerequisite itself 2-3 days. Later on only we will go to the PAM4. Hope from the session today. From junior to senior. Okay. Anything you want to add on the questionnaire?
I may want to share the survey questions now tomorrow, sir.
Gauri, we can share it later, Gauri. I think 7 o'clock now.
Okay,
So,
yeah.
Send the questionnaire, right? It's a mandatory requirement for you to reply for this questionnaire, right? And then after the questionnaire, and then we, based on the, even if you have more questions, you tell us in the offline. We will discuss about all those questions tomorrow, and then we'll start with the video. Then we will go to the chapter.
yeah. So yes, Jagdish. Yeah, we start with Q&A and videos tomorrow, so that we can refresh this, and then we can go to the next chapters. Yeah, that will help actually. Yeah.
Okay, feel free to give the right comment, right feedback on this one. Okay. Thank you.
Thanks, Jagdish. Thanks, Gauri.
Thank you.